Hello there, and welcome to the Cosmographer. The edge of the observable universe sits 46.5 billion light-years from the room you are lying in, and every instrument humanity has ever built goes blind there. Tonight, across 3 unhurried hours, we are counting down the 10 most disturbing answers physics has ever offered to one question: what sits on the other side of that line? A team at NASA once measured hundreds of galaxy clusters sliding at 2 million miles per hour towards something beyond the horizon, something no telescope can ever show us. The James Webb Space Telescope recently photographed 263 ancient galaxies, and 2/3 of them spin the same way, exactly what a universe born inside a black hole would look like. And our own particle physics quietly insists that the vacuum of space is provisional, and that somewhere past the edge, its replacement may already be traveling. 10 theories, ranked by how deeply each unsettles the picture of reality. And the one at the very top does not place anything beyond the edge at all. It takes something away instead, something you have believed your entire life. Get comfortable and settle in. If you enjoy falling asleep to the universe's biggest questions, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the edge of the universe will not be where you left it. Let's begin at number 10. Number 10. More of the same, forever. This is a list of 10 theories about what sits beyond the edge of the universe, and it is worth 3 unhurried hours because the question behind it is the oldest one we have. Every person who has ever looked up at a night sky has, at some point, wondered where it all stops and what is standing on the far side when it does. Tonight we are going to take that question seriously, at full length, with the actual physics, the actual names, and the actual numbers. Some of the answers on this list are unsettling in a quiet way. 1 or 2 of them are unsettling in a way that may stay with you. And the theory waiting at number 1 is, in its own gentle fashion, the most disturbing of them all, precisely because of what it takes away. Before we begin the descent, we should set the stage carefully, because the word edge is doing a lot of work in that title. The universe we can observe is a sphere, roughly 93 billion light-years across, centered on us. Its radius, the distance from your bedroom to the farthest thing we can in principle see, is about 46.5 billion light-years. Hold on to that number, because it is the biggest one this night owns, and it will come back before we are done. Inside that sphere sit an estimated 2 trillion galaxies, a figure astronomers arrived at in 2016 by counting the faint smudges in deep images from the Hubble Space Telescope and extrapolating downward to the galaxies too dim to see. 2 trillion is roughly 250 galaxies for every living human being. Each of those galaxies holds, on average, 100 billion stars or more. That is the inventory of everything we can ever examine, and it is almost certainly not the inventory of everything there is. The universe is 13.8 billion years old, and a careful listener will notice a problem in the numbers I just gave. If the cosmos has only existed for 13.8 billion years, light should only have had time to cross 13.8 billion light-years, and yet I claimed we can see more than 3 times farther. The resolution is that space itself has been expanding the whole time the light was in flight. A photon that left a young galaxy 13 billion years ago has been swimming toward us while the ocean beneath it stretched. By the time it arrives, the shore it left is no longer 13 billion light-years away, but more than 40 billion, carried outward by the expansion of space itself. Nothing moved through space faster than light. Space simply grew, and it is allowed to grow at any rate it pleases, because the speed limit applies to things in space, not to space itself. That is why the edge of the observable universe is not a wall. It is a horizon of light. It marks the distance from which light has had time to reach us since the beginning, and nothing more. There is no fence there, no membrane, no signpost. A galaxy sitting exactly on our horizon is an ordinary galaxy, going about its ordinary business, and an astronomer living in that galaxy sees no edge at their own address at all. They see their own sphere of 93 billion light-years centered on themselves, and it reaches 46.5 billion light-years beyond anything we will ever observe. Every point in the universe is the center of its own observable universe. The edge is not a place you could travel to. It travels with you, the way the horizon at sea retreats ahead of a ship, always the same distance away, always promising a boundary that is never actually there. There is, however, a second horizon, and this one is crueler. Because the expansion of the universe is accelerating, a discovery made through distant supernova measurements in 1998, there is a distance beyond which light leaving a galaxy today will never reach us, no matter how long we wait. That boundary, called the cosmic event horizon, sits roughly 16 to 18 billion light-years out. A galaxy beyond that line could hold the most important object in all of existence, and a civilization there could aim its brightest beacon directly at us and hold it steady for 1 trillion years, and the signal would still lose the race, because the space between us grows faster than light can close the gap. Their message is a postcard that can never arrive. Ours to them is the same. Most of the universe, even most of the universe we can currently see, has already passed beyond the reach of any reply. So this is the honest shape of our situation. We live inside a sphere of light on an ocean whose true size is unknown and quite possibly unknowable. Everything beyond the sphere is invisible to us, not because it is hidden, but because the universe has not existed long enough and will not cooperate long enough for its light to make the trip. And yet physics does not fall silent at the horizon. The same equations that describe everything inside the sphere have things to say about what should lie outside it. Every theory on tonight's list is an attempt to say what the light cannot. Some are conservative extrapolations that most cosmologists would sign. Some are contested claims with careers staked on them. Some are speculations from the far end of serious theory, and as we go, I will always tell you which is which. The list is ranked from number 10 down to number 1 by how deeply each answer unsettles the picture of reality you carried into this video. We begin with the answer that sounds the most reassuring, and is not. The most conservative answer to the question of what sits beyond the edge is simply this: more. More universe, more galaxies, more of the same, continuing on without end. No new physics, no exotic structures, just the cosmos we already know, extended past our horizon the way the Pacific extends past the view from a California beach. Most cosmologists, asked to bet, would put their money here. And the disturbing part is what the word endless does when you take it literally, because if the plainest reading of our best data is correct, then somewhere out there in the more, there is another you, listening to another version of this exact sentence, and the mathematics does not merely permit that. It requires it. The case starts with a measurement. The Planck satellite, a European mission that spent 4 years mapping the cosmic microwave background, the oldest light in existence, gave us, in its final 2018 analysis, the most precise measurement ever made of the universe's overall shape. Space could have been curved like a sphere, so that parallel lines eventually meet and the cosmos closes in on itself with a finite volume. It could have been curved like a saddle, with parallel lines forever spreading apart. Or it could be flat, in the geometric sense, with parallel lines running parallel forever. Planck's answer, sharpened by surveys of how galaxies cluster, is that the universe is flat to within about 1/10 of 1%. If that flatness is exact, and if space is simply connected, meaning it does not loop around on itself in some clever way we will discuss at number 9, then the universe is infinite, not enormous. not astronomically large. Infinite, in the full mathematical sense of the word, with no last galaxy and no final light. Infinity is a concept our minds handle badly, and cosmologists handle it with arithmetic instead of intuition. Here is the arithmetic that matters. Take a region the size of our observable universe, a sphere 93 billion light-years wide. Ask how many distinct ways the matter and energy inside such a region can be arranged, down to the quantum level, counting every possible position and state of every possible particle. The answer is a finite number. It is a preposterous number, roughly 10 raised to the power of 10 to the power of 122, a figure so large that the universe does not contain enough matter to write it down in ordinary digits. But it is finite, and that is the hinge on which everything turns. An infinite universe contains infinitely many regions that size, infinitely many drawers, filled from a catalogue with finitely many patterns. The conclusion is not optional. Patterns must repeat. Every possible arrangement of a region that size, including the one you are lying in right now, occurs not once, but an infinite number of times. It is fair to ask how anyone measures the shape of everything from the inside, and the method is elegant enough to be worth a minute of our 3 hours. The cosmic microwave background is a snapshot of the universe at 380,000 years old, and the physics of that era set a natural yardstick, a preferred size for the hot and cold blotches frozen into the glow. Theorists can compute how large those blotches should appear on our sky if the light from them traveled through flat space, like lines drawn on a stretched sheet. If space were curved like a sphere, the blotches would look larger than the flat prediction, magnified as though through a lens. If space were curved like a saddle, they would look smaller. The Planck satellite measured the blotches across the entire sky with microkelvin precision, and they are, within that 0.1%, exactly the size flat geometry predicts. It is the same trick a surveyor uses, drawing a triangle and checking whether its angles total 180 degrees, performed on a triangle whose sides are 45 billion light-years long. The counting argument deserves one honest comparison too, because 10 to the power of 10 to the power of 122 is not a number so much as a place where numbers stop meaning anything. The total count of atoms in the observable universe is about 10 to the 80th. The number of seconds since the Big Bang is about 400 quadrillion, a number with only 18 digits. The number of possible games of chess, often quoted as the largest number in casual use, has around 120 digits. The number of quantum states available to a region the size of our observable universe has more digits than there are atoms to ink them with. And yet the crucial word in that sentence is not large. The crucial word is finite. A draw catalogue with a Google of Googles of patterns is still a catalogue, and infinity is patient enough to exhaust any catalogue, then exhaust it again, forever. Mathematicians have understood this since long before cosmology could use it. When the page never ends, no pattern on it gets to be rare. There is also a quieter observation hiding in the flatness result, one that cosmologists mention with a certain professional discomfort. Of all the shapes the universe could have taken, exact flatness is the knife's edge, the single special case balanced between closing in on itself and splaying open. Finding the cosmos parked on that edge, to a 0.1% after 13.8 billion years of expansion that should have amplified any early tilt enormously, is either a coincidence of cosmic proportions or the signature of a mechanism that flattened everything at the start. That mechanism is inflation, and we will meet it soon, because inflation does not only iron the universe flat, it also, almost as a side effect, manufactures other universes, and that is a matter for number 6. This line of reasoning has a respectable pedigree. The cosmologists George Ellis and Gordon Brundrit worked through the logic in 1979 in a paper that calmly pointed out that an infinite universe with the properties we observe implies infinitely many inhabited planets, infinitely many civilizations, and infinitely many beings indistinguishable from ourselves. Decades later, the physicist Max Tegmark put actual distances on the idea, and his numbers have become the standard way of feeling the weight of it. On average, Tegmark estimated, you would need to travel about 10 to the power of 10 to the power of 29 meters to find an exact copy of yourself, a person whose every particle, every memory, and every half-formed thought about this video matches yours precisely. To find an exact copy of our entire observable universe, every galaxy and place, every war fought the same way, every childhood identical down to the weather on your first day of school, the average distance rises to about 10 to the power of 10 to the power of 115 meters. These numbers are so large that the choice of units is a joke the mathematics plays on us. Measure in meters or in light years, it makes no visible difference to the exponent. Writing the smaller of the two numbers out in ordinary digits would require more zeros than there are atoms in the observable universe, and the atom count is itself a 1, followed by about 80 zeros. It is worth pausing on what this theory does not claim. It does not claim a mystical connection between you and your copies. It does not claim you could ever meet one, since even the nearest copy lies unimaginably far beyond the event horizon, in a region whose light will never reach your descendants, however many of them there are. It claims something more clinical and, in its way, colder. It claims that you are a pattern, that patterns in a finite alphabet repeat when the page is infinite, and that the universe, on its plainest reading, is an infinite page. Tegmark called this the level 1 multiverse, the most modest rung on his ladder of multiplicity, because it invents nothing new. Same physics, same particles, same laws. Just more space than the concept of you can stay unique in. Now for the honesty the claim deserves, because this is a list that will always tell you where the ice is thin. The measurement of flatness is a measurement with error bars, and flat to within 0.1% is not the same as exactly flat. The universe could be very slightly curved, closed like a sphere, so colossal that our whole observable cosmos sits on it, like a coin on the surface of the Earth. And in that case, the total volume is finite, and the copies are not guaranteed. The argument also assumes that matter beyond our horizon is spread more or less the way it is here, that our patch is typical rather than special. Inflation, the theory of the universe's first instant that we will meet properly at number 6, supports that assumption, but supports is not proves. And philosophers of physics point out a genuine technical wound called the measure problem, which is that probability itself becomes slippery when you try to do statistics over an infinite sample. So the copies are not a certainty. They are the default output of our most straightforward data, taken at face value, and cosmologists disagree mainly about how seriously to take the face value. Still, sit with the plainest version for a moment, because this is the gentlest item on tonight's list, and it deserves its full weight before we move on to stranger things. If the flat, infinite reading is right, then beyond the edge of everything we can see, the universe holds every version of your life. There is a copy of you who took the job, and a copy who never left, and a copy for whom this night ended differently in every way a night can end. Each of them is as real as you are, made of the same kinds of atoms obeying the same laws, and each is permanently unreachable, sealed away not by a wall but by sheer distance and the arithmetic of light. Somewhere beyond the horizon, on this theory, every choice you did not make was made, and there is no way, even in principle, to visit, to warn, or to envy. The infinite universe keeps perfect archives and allows no interlibrary loans. There is one more feature of this picture worth naming before we descend a step. In an infinite universe of repeating patterns, the question what sits beyond the edge has a strangely bureaucratic answer. Beyond the edge sits another observable universe, much like ours, centered on someone else. Beyond theirs, another. The cosmos becomes an endless quilt of overlapping spheres of light, each one a private cosmos for whoever stands at its center, no sphere privileged, no sphere final. It is democracy at a scale that erases meaning. Nothing is central, nothing is rare, and nothing, anywhere, is the only one of itself. But infinity repeating is only the gentlest possibility, the one that leaves the map intact and merely extends it forever. The next theory on the list quietly folds the map instead. It says that if you built the fastest ship in history and sailed it in a perfectly straight line toward the edge of the universe, refusing every turn, you would not find a wall, and you would not find endless new territory either. You would, after an unthinkable stretch of time, find yourself arriving somewhere you have already been. Number 9. The universe that wraps around. The theory at number 9 begins with a distinction most of us never have a reason to learn: the difference between the shape of space and the connections of space. Everything we said at number 10 about flatness concerned geometry, the local rules for triangles and parallel lines. But geometry does not settle how space is wired together on the largest scale, a property mathematicians call topology, and this loophole is wide enough to drive a universe through. A sheet of paper is flat. Roll it into a cylinder, and every triangle drawn on it still behaves exactly as it did before. Every angle sum still comes out to 180 degrees, and yet an ant walking a straight line around the cylinder comes home. Flat geometry, looped connections. General relativity, the theory that governs cosmology, dictates the geometry of the universe and says absolutely nothing about its topology. Einstein's equations would be perfectly satisfied by a cosmos that folds back on itself, and we would have measured it as flat all the same. This possibility is older than general relativity itself. In 1900, the astronomer Karl Schwarzschild, whose name now marks the boundary of every black hole, gave a lecture in which he asked his audience to imagine that space might be finite and multiply connected, so that a traveler flying straight ahead, never turning, would eventually see the lights of home rising in front of them. He was speculating decades ahead of the mathematics that could support the idea, and he knew it, but the question he asked has never been closed. The modern version usually takes the form called a 3 torus, which you can picture as a cosmic box, perhaps some tens of billions of light-years on a side, whose faces are glued to their opposites. Exit through the ceiling, and you re-enter through the floor. Exit through the north wall, and you return through the south. Players of old arcade games know this space intimately. It is the world of the wraparound screen, where a ship flying off the right edge reappears on the left, and nothing anywhere feels like an edge from the inside. A universe wired this way would be finite, with a definite total volume and a countable number of galaxies, and yet it would have no boundary at all. No wall, no rim, no last shelf of stars with darkness behind it. The question what sits beyond the edge would fail in the friendliest possible way, because every direction would eventually lead back through territory already mapped. And the theory makes a prediction so strange it sounds like folklore. If the loop was small enough, light could lap the universe. Photons leaving the Milky Way could travel the long way around the cosmos and arrive back where they started, which means that somewhere out there among the distant galaxies in our telescopes, we could be looking at our own galaxy, seen from behind, its light delayed by billions of years spent circling existence. The sky could contain ghost images, the same objects appearing in different directions at different ages. Somewhere in our deep field photographs, unrecognized, could hang the Milky Way's own baby picture. Imagine the voyage directly, because this is one of the few items on tonight's list you can walk through. You are aboard a ship with engines beyond any physics we own, pointed at a fixed star field, holding a line so straight that a laser could not fault it. The Milky Way falls behind and dims to a smudge, then to nothing. Millions of years pass in the dark between galaxies. Whole clusters drift by like distant harbor lights and are gone. You keep the bow steady for so long that the ship's records of home become mythology, and still there is no wall ahead, no thinning of the stars, no sign the universe is running out. Then, in the far distance, a faint spiral begins to gather itself out of the black. It grows for 10,000 generations. Something about the tilt of its arms is familiar in a way that raises the hair on your arms. And as the spiral fills the viewport, resolving into star clouds your ancestors had names for, you understand that the straight line was a circle all along. You have not found the edge of the universe. You have come home, approaching from the far side, and the journey's only discovery is that there was never anywhere else to go. The remarkable thing is that this romantic-sounding idea comes with a hard experimental test, and the test has actually been run. If the universe loops on a scale smaller than the observable sphere, then the cosmic microwave background, that oldest light we keep returning to, must carry a specific fingerprint. The glow we observe comes from a spherical shell around us, the surface of last scattering. In a wrapped universe, that sphere can be larger than the fundamental cell of space itself, which forces the sphere to intersect its own copies. The geometry of those self-intersections is a set of circles, and the temperature patterns around any such circle would appear twice, in two different places on our sky, matched point for point like two prints of the same negative. The matched circle test was not the first attempt to catch the universe repeating itself. Astronomers had already tried a more direct approach, sometimes called cosmic crystallography, which treats the deep sky as a possible hall of mirrors and hunts for the reflections one by one. If space loops, then a sufficiently distant quasar might appear twice on our sky, in different directions, at different ages, the way a candle between two facing mirrors becomes a corridor of candles. The trouble is recognition. A galaxy seen from behind, 5 billion years younger, does not resemble its present-day portrait any more than a baby photograph resembles the adult, and the universe offers no name tags. Searchers instead looked for statistical repetitions, for the same spacing patterns among clusters showing up in more than one region, and they found nothing convincing. The hall of mirrors, if we are in one, keeps its reflections too far apart and too disguised to identify. There is a deeper history here as well, because the question of whether the universe closes on itself is as old as modern cosmology. When Einstein applied his brand new general relativity to the whole cosmos in 1917, the very first relativistic model of the universe he built was finite and unbounded, a three-dimensional sphere in which a straight path returns to its origin. He chose that shape partly for philosophical comfort, a universe complete in itself, needing no edge and no beyond. The expanding models that replaced his static cosmos kept the option open, and the mathematician Alexander Friedmann, who first derived an expanding universe from Einstein's equations in 1922, treated closed and open cases with equal seriousness. The founders of the field, in other words, considered a universe without an outside to be not an exotic loophole, but a live and even elegant possibility. What changed is only that we learned to measure, and the measurements pushed the loop, if it exists, beyond our sight. Consider, for the pleasure of it, what living in a genuinely small wraparound universe would have been like. Suppose the fundamental cell were only 100 million light-years wide, far smaller than the observable sphere. Our night sky would then be an onion of self-portraits. The nearest layer would show the Milky Way and its neighbors as they looked 100 million years ago, in every direction at once. Behind that, a shell of images 200 million years old, and behind that another, deeper and younger, layer upon layer, the same finite furniture photographed at every age back to its infancy. Astronomy in such a cosmos would be a kind of archaeology of the self. Astronomers could watch their own galaxy form by looking farther away, could calibrate their entire history against repeated images of home, and would have known from the first telescopes that the universe was a closed and countable place. The strangeness of our actual situation is that we could still be in a version of that universe, merely one size too large to catch, and the sky would look no different than it does tonight. Schwarzschild himself, back in 1900, put a flaw under the idea with the data of his day, estimating that if space wrapped, the loop had to be at least many hundreds of light years across, because surveyors of the sky had seen no duplicate stars. The flaw has been rising ever since, from hundreds of light years to millions to billions, each better map pushing the possible seam farther out, and the pattern of that retreat is itself the story of this item. The wraparound universe has never been ruled out. It has only ever been ruled larger. There is a version of scientific patience in which that counts as progress, and a version of cosmic humor in which the universe keeps its most elegant secret by holding it always one map beyond the newest map we make. It is worth being concrete about what the modern data demand of a wraparound cosmos. The observable sphere is about 93 billion light-years across, and the absence of any repeated pattern within it means the fundamental cell of space must be at least comparably large, and likely larger. A 3 torus just beyond that limit would still be a finite universe, with a total volume perhaps a few times that of everything we can see, holding a countable number of galaxies, a number with a final digit. Somewhere in such a cosmos there would be a largest structure, a most distant pair of objects, a completed inventory. Nothing in physics forbids it. The universe could be a box of definite size, wrapped so that no wall is ever met, and we would see exactly what we see, a flat, seamless sky with the seams hidden one size beyond the horizon. The definitive test, then and now, remains the circles in the ancient light. The search for those matched circles was proposed in 1998 by 3 cosmologists, Neil Cornish, David Spergel, and Glenn Starkman, and it is a beautiful piece of scientific thinking because it converts a question about the wiring of all existence into a pattern-matching exercise a computer can run. Take the full-sky microwave maps, compare the temperature profile around every possible circle with every other possible circle, in every orientation, at every size, and see whether any pair agrees far beyond chance. The computation is enormous, billions upon billions of comparisons, and it has been performed on the maps from the WMAP satellite, and again, more stringently, on the sharper maps from Planck. The result was silence. No matched circles, anywhere, at any scale, to the limits of the data. The universe declined to show us its seams. Silence, in science, is still an answer, and the answer here has a precise shape. The absence of matched circles does not prove the universe is simply connected. It proves that if the universe loops, the loop is larger than the observable sphere, so that the surface of last scattering never intersects its own copies. The fundamental cell, the true repeating unit of the cosmos, would have to be wider than what we can see, which places the wraparound, if it exists, permanently beyond the edge, hidden by construction, forever one size larger than our vision. There is something almost sly about that outcome. The one theory on tonight's list that promised the sky itself could confirm it has arranged matters so that the confirmation lies just out of reach. The idea has refused to die completely for one further reason: a set of genuine oddities at the largest scales of the microwave sky. The very broadest ripples in the cosmic glow, the patterns spanning the widest angles, are measurably weaker than standard cosmology predicts, as though the universe ran out of room for its largest waves. A finite, wrapped cosmos would do exactly that, cutting off wavelengths longer than its own size, the way a violin string cannot sound a note longer than itself. In 2003, the cosmologist Jean-Pierre Luminet and his colleagues proposed a specific candidate, the Poincaré dodecahedral space, a universe tiled from a gently curved 12-faced cell, a cosmic soccer ball whose size matched the missing ripples surprisingly well. The dodecahedral universe predicted its own matched circles, the searches came up empty, and the proposal faded to a footnote. But the missing large-scale power is still in the data, along with a strange alignment of the biggest patterns that astronomers half-jokingly named the axis of evil, and nobody has fully explained either one. They are probably statistical flukes. Probably. Notice what this theory does to the psychology of the question we are spending the night on. Every other item on this list populates the beyond with something: more space, other universes, stranger machinery. The wraparound universe answers the question by abolishing the destination. What sits beyond the edge of the universe? You do. The far side of the cosmos is the back of your own head. The deepest image in our telescopes might be our own neighborhood in ancient light, and the darkness out past the last visible galaxy might be, in the most literal sense, the space behind you. It is the gentlest disturbing answer imaginable, a cosmos that is finite, self-contained, and haunted only by its own reflections, a house of mirrors with no exit, because no exit is needed. A universe that folds back on itself would at least be tidy, a sealed room with nothing outside its walls because its walls face each other. The next item on this list is not tidy. It is the moment tonight's question stops being philosophy, because it concerns an actual measurement, made with real satellites by a real team at NASA, which seemed to show 1,000 galaxy clusters sliding together across the sky, all in the same direction, as though something on the far side of the edge had taken hold of everything we can see and begun, very patiently, to pull. Number 8. The dark flow. The theory at number 8 begins with an uncomfortable fact about our own motion. Nothing in the universe sits still. The Earth circles the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 230 kilometers per second. The Milky Way itself is falling toward our neighbor Andromeda, and the whole local group of galaxies, our gravitational household, moves at roughly 630 kilometers per second relative to the one truly universal reference frame we possess, the cosmic microwave background itself. We know this because our motion prints a signature on the ancient light. The half of the sky we are moving toward glows very slightly warmer, and the half behind us very slightly cooler, a Doppler blush called the dipole, and it is one of the most precisely measured quantities in all of cosmology. None of that troubles anyone, because all of it has visible causes. The pull of Andromeda, the mass of the Virgo cluster, the enormous concentration of galaxies called the Great Attractor that hides behind the dusty plain of our own galaxy, and beyond it the even larger Shapley supercluster, hundreds of millions of light-years away. In 2014, the astronomer Brent Tully and his colleagues mapped the full basin of these flows and gave our home supercluster a name, Laniakea, a Hawaiian word meaning immense heaven, a watershed of 100,000 galaxies 500 million light-years wide, all drifting slowly down the same gravitational valley. Motion with a visible cause is just weather. The cosmological principle, the founding assumption that the universe on its largest scales is the same everywhere and pulls in no preferred direction, allows local weather. What it forbids is a wind that blows the same way across the whole of the sky. In 2008, a team at NASA's Goddard Space Flight Center reported exactly that forbidden wind. The team was led by Alexander Kashlinsky, an astrophysicist who had spent years developing methods for reading faint signals in the cosmic microwave background, working with Fernando Atrio Barandella of the University of Salamanca and the astronomers Dale Kochevsky and Harold Eberling. They were not measuring nearby galaxies, where local weather rules. They were measuring the motion of entire clusters of galaxies, the largest bound objects in existence, each one a swarm of hundreds or thousands of galaxies wrapped in gas heated to tens of millions of degrees, spread across billions of light-years of sky. And what they found, they claimed, was that the clusters were not drifting randomly, each answering its own local geography. Hundreds of them appeared to be streaming together, coherently, in a single direction, toward a patch of southern sky between the constellations Centaurus and Vela. The speed they measured was somewhere between 600 and 1,000 kilometers per second, which is around 2 million miles per hour. The direction was consistent no matter how far out they looked, and in a follow-up study in 2010, using roughly 1,400 clusters, the flow appeared to extend to at least 2.5 billion light-years, with no sign of dying away with distance. That refusal to fade was the alarming part. A flow caused by anything inside our observable universe, some enormous concentration of mass in one direction, should weaken as you survey volumes larger than the cause. This one seemed not to. It behaved less like a current stirred by something in the ocean, and more like the whole ocean itself, sliding, basin and all, toward a destination the map does not contain. Kashlinsky's team gave the phenomenon a name that has kept its chill ever since. They called it the dark flow. The claim deserves a moment of respect before we examine it, because of what it would mean if true. Every cluster of galaxies we can see shares, on this measurement, a common motion with no visible source. The cosmological principle does not permit that, unless the source lies where we cannot check, beyond the horizon of light. And so the dark flow became, for a few years, the closest thing modern cosmology has ever had to a direct observation of the beyond, an arrow drawn across our entire sky, pointing at something outside everything. Before we weigh the evidence, it helps to know that heretical flows have a history in astronomy, and the history cuts both ways. In 1976, Vera Rubin, the astronomer whose galaxy rotation work would later make dark matter unavoidable, reported with her colleague Kent Ford that a sample of distant spiral galaxies seemed to share a large coherent motion across the sky. The claim, which became known as the Rubin-Ford effect, was received coldly, criticized on statistical grounds, and set aside for years. Rubin later recalled it as one of the episodes that taught her how a field treats results it is not ready for. And yet, by the late 1980s, a collaboration of 7 astronomers, nicknamed the 7 Samurai, found through independent methods that our entire region of the universe really is streaming at hundreds of kilometers per second toward a mass concentration they named the Great Attractor, in almost the same quarter of the sky Rubin had indicated. The specific numbers had problems, but the phenomenon of large-scale bulk flows turned out to be entirely real. The lesson goes in both directions at once. Flows that sound impossible are sometimes artifacts, and flows that get dismissed are sometimes the map's next feature, waiting for better instruments to make them respectable. The difference between those historic flows and the dark flow is a matter of reach, and the reach is everything. The Great Attractor and the Shapley concentration behind it live a few 100 million light-years away, safely inside the observable universe, and the motions they cause fade with distance, exactly as gravity says they should. They are weather within the map. The dark flow claimed to be something categorically different, a motion that did not fade across billions of light-years, implying a source too far away to fade, which is to say a source outside the map entirely. Cosmologists had a term ready for the general idea long before the measurement. A universe given one shared push at birth is called a tilted universe, and theorists in the early 1990s had already worked through what such a tilt would imply, treating it mostly as an exercise. The dark flow was the moment the exercise appeared to file a report from the actual sky. It is also worth knowing that the broader question, whether the universe pulls perfectly evenly on the largest scales, has stayed genuinely alive in other data even after the dark flow faded. The dipole in the cosmic microwave background is assumed to be purely our own motion, and if that is right, the same dipole should appear, with a predictable strength, in counts of distant radio galaxies and quasars across the sky. Several independent analyses of large quasar and radio catalogs have found dipoles pointing in the expected direction but noticeably stronger than the prediction, a discrepancy that has persisted at uncomfortable significance for years and has no agreed explanation. It may be a subtlety of the catalogs. It may be a hint that the largest scales are not quite as even-handed as the founding assumption requires. No one currently claims it is a hand reaching in from beyond the horizon, but the file on cosmic evenness is not as closed as textbooks make it sound, and every crack in that file is a crack the dark flow's ghost can whisper through. Hold all of that context, the vindicated heresies and the artifacts, the live tensions and the settled weather, as we return to the measurement itself, because the dark flow's fate turned entirely on the craft of extracting 1/1,000,000th of a degree from maps that never stop humming. To judge the claim, you have to understand how anyone measures the speed of a galaxy cluster billions of light-years away, because the method is one of the most delicate ever attempted, and its delicacy is where the whole controversy lives. You cannot simply watch a cluster move. At those distances, a cluster could travel at 1,000 kilometers per second for 1,000,000 years, and its position on our sky would not shift by any measurable amount. Instead, Kashlinsky's team used an effect predicted in the 1970s by two Soviet physicists, Rashid Sunyaev and Yakov Zeldovich. The hot gas filling a galaxy cluster is a fog of free electrons, and photons of the cosmic microwave background must fly through that fog on their way to our telescopes. If the cluster is moving relative to the background, the electrons impart a whisper of that motion to the light, shifting its temperature by about 1/1,000,000th of a degree. The moving cluster, in effect, leaves a faint smudged fingerprint on the oldest light in the universe, and the direction of the smudge records the direction of the motion. 1/1,000,000th of a degree is far too faint to read from any single cluster, so the team stacked. They took the positions of roughly 700 clusters known from X-ray surveys, laid the corresponding patches of the WMAP satellite's microwave maps on top of one another, and searched the combined signal for a common tilt. Stacking is a standard and honorable technique. It is how faint signals are pulled from noise across all of astronomy. But everything depends on the filtering, on how you remove the far larger signals that sit in the same maps, the intrinsic ripples of the background itself, the glow of our own galaxy, the thermal signature of the cluster gas. The dark flow lives or dies inside those filtering choices, a signal the size of 1/1,000,000th of a degree, extracted from maps whose other features are thousands of times larger. Kashlinsky's team published their pipeline, defended it in detail, and reported that the tilt was there, consistent across independent groups of clusters, pointing at Centaurus. Now imagine the view from inside the phenomenon, if it is real. You are standing on a rocky world in one of those clusters, 2 billion light-years from Earth, under a sky crowded with the smeared golden lights of 1,000 neighboring galaxies. Nothing feels wrong. There is no wind, no lean, no hum in the ground, because gravity's pull is perfectly uniform across you, your planet, and every star you can see, and a uniform pull is indistinguishable from no pull at all. And yet everything in your sky, every galaxy, every filament of gas, the entire luminous inventory of your existence, is sliding at 2 million miles per hour toward a single point in the darkness, and has been since before your star was born. You could live and die on that world, build observatories, map your cosmos to its horizon, and never once detect the current carrying it all, because the current carries your rulers and your clocks along with it. The flow would be visible only to someone comparing your motion against the one light that does not travel with you, the ancient glow behind everything. From inside, the most complete journey in the universe feels exactly like standing still. What could possibly cause such a thing? Kashlinski's own interpretation reached beyond the horizon. In the standard story of inflation, the universe we see was smoothed and flattened in its first instant, but the smoothing only guarantees uniformity out to scales somewhat larger than what we observe. Farther out, the primordial landscape could be as lumpy as it likes, and a truly enormous concentration of mass sitting beyond our horizon since before inflation ended would tilt our entire observable patch, imparting one shared motion to everything inside it. We could never see the mass itself. Its light will never reach us. We would know it only the way a sleeping passenger knows the sea, by the slow lean of everything around them. The physicist Laura Mersini-Houghton went further still, arguing that a coherent tilt of exactly this kind is what you would expect if our universe carries the gravitational imprint of a neighboring universe, a pull inherited from the multiverse we will meet at number 6. On either reading, the dark flow was advertised as something almost unprecedented in science, an empirical handle on territory that is, by definition, unobservable. Then came Planck. The European successor to WMAP flew with better detectors, sharper resolution, and lower noise, and it carried its own science team with its own filtering pipeline. In 2013, the Planck collaboration published a dedicated analysis of cluster motions using their superior maps, and their conclusion was flat. They found no significant coherent flow. Their upper limit said that if the clusters share any common drift at all, it is slower than about 250 kilometers per second, well below the 600 to 1000 that the dark flow claimed. In the currency of cosmology, that verdict from that instrument was close to a closing argument. Most of the field filed the dark flow away as a cautionary tale about faint signals and ambitious filtering, and moved on. But the story did not close cleanly, and the reason it did not is worth your attention, because it says something about how science actually behaves at its edges. Kashlinski and Atrio Barandella did not concede. They published responses arguing that the Planck team's filtering was the flawed one, that it erased exactly the long wavelength component in which the flow lives, that finding nothing after removing the signal is not the same as the signal being absent. The Planck side considered the matter settled and largely declined to continue the argument. And so the dark flow entered the strange afterlife, where contested results go, not confirmed, not formally retracted, defended by the people who found it, and dismissed by the wider field. Two careers, in particular, remain quietly staked to an arrow on the sky that the community has voted away. There is something worth sitting with in that image, a scientist spending years developing the tools to hear a whisper, hearing it, reporting it, and then watching the field's biggest instrument declare the whisper silence. Whichever side is right, that costs something, and the cost is paid in the only coin a scientist has, the years of a working life. Where does the evidence sit tonight? Honestly, and this list will always be honest with you, the dark flow is probably not real. Newer and independent measurements lean against it. Large compilations of supernova distances, the same kind of data that revealed cosmic acceleration, have been used to test whether the local universe shares any anomalous bulk motion, and they find the expansion looking clean and uniform once known local flows are accounted for. No independent team has reproduced the dark flow with post-Planck data. The most probable resolution is that the signal was an artifact living in the seams of the analysis, a ghost conjured from a millionth of a degree. That is the sober verdict, and you should carry it with you through everything that follows. And yet the dark flow, earns its place high on tonight's list for one reason that survives its own probable death. It taught cosmology something uncomfortable, which is that the beyond is not necessarily mute. Before 2008, what sits outside the horizon was a question for philosophers, unanswerable by construction. The Dark Flow episode demonstrated that an outside structure, if one exists and is large enough, would leave exactly this kind of fingerprint, a coherent drift of everything visible, sourced by nothing visible. The claim may have failed, but the category of the claim is permanently open. If something with sufficient mass sits beyond the edge of the universe, this is how it would announce itself, not with a light in the sky, but with a lean in the dark. Astronomers now know what such an announcement would look like, and they know that nothing in physics forbids one. The observation was probably wrong. The possibility is not. Consider what it would mean for you, personally, if the arrow turns out to be real after all. Every atom in your body, every photon your eyes will ever catch, every place you have ever been and everyone you have ever known would be aboard the same silent current, bound for a destination on the far side of the sky's oldest light. No one will ever see the destination. No signal from it can arrive, and none of ours can be delivered. The source of the flow would be a return address on mail that cannot be sent, a postcard that can never arrive, written from a place that our universe can feel but never once be shown. Everything you know might be en route to somewhere, and the somewhere is permanently none of our business. Whatever the final truth of the flow, notice what kind of answer it gave to tonight's question. It treated the beyond as a place, a location in space with mass and a direction, tugging on the visible world the way an unseen moon tugs a tide. The next theory on the list refuses even that much familiarity. It says the beyond is not somewhere else at all. It says the beyond is someone else, that outside our universe in the direction of the past sits the cooling corpse of a previous one, and that the far future we are drifting toward is somebody else's Big Bang. Number 7. The corpse of a previous universe. The theory at number 7 asks you to stop thinking of the beyond as a direction you could point to, and start thinking of it as a chapter you cannot page back to. It comes from Roger Penrose, and before we take the idea itself seriously, it is worth knowing exactly who is proposing it, because this is not a speculation from the margins. Penrose is the mathematical physicist who proved, in 1965, that black holes are not exotic special cases, but unavoidable consequences of general relativity, work for which he shared the Nobel Prize in Physics in 2020. He gave us the mathematics of singularities, co-developed with Stephen Hawking, the theorems showing our universe must have had a beginning of some kind, and has spent 7 decades inventing tools the entire field now works with. When a mind of that caliber, in the last act of a monumental career, points at the sky and says the universe before ours may still be visible, the claim deserves a careful hearing, whatever its eventual fate. His proposal is called conformal cyclic cosmology, and it begins at the end of everything. Follow our universe forward, not millions or billions of years, but through the full run of its future. The stars burn out, the last red dwarfs guttering after trillions of years. The galaxies go dark, their remains spiraling slowly into the great black holes at their centers. And then, across a stretch of time that makes everything before it a rounding error, the black holes themselves evaporate, leaking away particle by particle through Hawking radiation, until after roughly 10 to the power of 100 years, a number with 100 zeros, the largest of them dissolve in a final flicker. What remains is the true end state, an expanse of cold, thin radiation, photons stretched to enormous wavelengths, sailing through a darkness that no longer contains anything else. No matter, no structure, no events. Just light, outliving everything light was ever meant to show. Here, Penrose notices something strange about that ending, and the strangeness is the hinge of the whole theory. Photons are massless, and massless particles do not experience time. Moving at the speed of light, a photon's clock does not tick, and with no mass anywhere, nothing in that final universe can function as a clock or a ruler at all. Time and size are measured by matter, by atoms vibrating and pendulums swinging, and when the last matter is gone, the universe loses the ability to know how large or how old it is. A cosmos containing only radiation is, in a precise mathematical sense, scale-free. And Penrose's observation is that the same is true of the other end of a universe's life. The Big Bang, an unimaginably hot, dense flood dominated by radiation, is also effectively scale-free, also a state where mass and measure lose their grip. The infinitely large, cold, empty end of one universe and the infinitely small, hot, dense beginning of another are, in the mathematics Penrose uses, the same kind of object. Strip away scale, which the universe itself has stopped keeping track of, and the two can be smoothly joined, the far future of one cosmos becoming the Big Bang of the next. On this picture, existence is a book of eons, each one a complete universe, running from its own Big Bang to its own cold conclusion, each conclusion opening directly onto the next beginning. There was a universe before ours. It lived, by our clocks, perhaps for a googol years. Its stars died, and its black holes evaporated, and its final sea of tired light became, without any bang or bridge, the blazing first moment of our own cosmos. And our future, the heat death waiting past the last black hole, is not an ending at all, but the quiet delivery room of the aeon after us. Beyond the edge of the universe, Penrose says, in the only direction that ultimately matters, lies the corpse of the previous universe, and we are lying in what will become the corpse that the next one is built from. The far future that Penrose builds on is worth touring slowly, because the numbers involved are the largest we will meet all night, and each one deserves its comparison. The era of stars, the entire age of shining that we think of as the universe's normal condition, lasts perhaps 100 trillion years, which sounds generous until you set it against what follows. 100 trillion years is to the age of the black hole era roughly what a single second is to a span unimaginably longer than the current age of the universe. After the last stars cool, the cosmos enters its long custodial phase, dead stellar remnants drifting, galaxies evaporating as gravitational encounters fling their corpses one by one into the dark. Much of the remaining matter finds its way, over these spans, into the supermassive black holes that anchored the galaxies, and then the waiting truly begins. A black hole with the mass of our galaxy's central giant, 4 million suns, takes something like 10 to the power of 87 years to evaporate through Hawking radiation. The largest holes, tens of billions of solar masses, hold out to around 10 to the power of 100 years. For comparison, the universe's current age, 13.8 billion years, is about 10 to the 10th. The gap between those exponents is not a quantity the human mind can hold. It can only be written down, and the evaporation itself is a miser's process. A large black hole radiates so faintly that for most of its life it absorbs more energy from the whisper-thin glow of space than it gives up, and only when the universe has dimmed below even that whisper does the whole begin, particle by particle, to spend itself. The final moments accelerate, the radiation sharpens, and the last instant releases a burst of energy, modest by cosmic standards, roughly comparable to a large thermonuclear explosion, the full stop at the end of an object that outlived everything else in existence. In Penrose's accounting, it is precisely these final punctuation marks, the last events that ever happen, that stand the best chance of printing through onto the next eon's sky. The Hawking points, if they are real, are not messages from the previous universe's prime. They are its very last words. Penrose's use of conformal geometry to join the aeons is less arbitrary than it may sound, because conformal structure is the part of geometry that light actually cares about. A conformal transformation rescales all distances while preserving every angle and every light path, and photons, having no clock and no ruler, live entirely within that angle and path skeleton. Penrose spent much of his career showing that the essential causal architecture of space-time, what can influence what, survives conformal rescaling untouched. His proposal simply takes that mathematics at its word. If the universe's final state contains only light, then the universe's final state carries only conformal structure, and nothing within physics prevents that structure from being read as the seed of a new expansion. The move that sounds like mysticism is, at the level of equations, an observation about what remains of geometry when the last clock leaves the room. Cyclic universes, it should be said, are an old dream with a famous wound, and part of conformal cyclic cosmology's appeal to its author is that it claims to heal it. The physicist Richard Tolman showed back in the 1930s that a universe which repeatedly collapses and rebounds should accumulate entropy from cycle to cycle, each bounce hotter and longer than the last, so that an eternal past of identical cycles is thermodynamically impossible. The old cyclic cosmos runs downhill. Penrose's version has no collapse at all, each aeon expanding forever into its successor, and it deals with the entropy ledger through the most contested move in the whole theory, the proposal that black holes, in evaporating, genuinely destroy the information, and with it, the entropy they swallowed, resetting the books for the next eon. Most quantum theorists hold information loss to be forbidden, and the modern consensus on the black hole information question leans hard against Penrose here. He has accepted that fight willingly, in his usual manner, one heresy defending another. He has even proposed that the dark matter of our universe consists of particles he calls erebons, named for Erebus, the Greek darkness, Planck-scale relics carried across the transition from the previous eon, decaying slowly in ours, a suggestion that would make most of the universe's mass a literal inheritance from the dead. Hold that ledger of audacities in mind, the erased information, the inherited darkness, the aeons filing forward without end, because it sets the stakes for the part of the theory that touches actual data. What separates this from pure philosophy is that Penrose insists the previous aeon should be visible, and he has spent years telling us where to look. Events titanic enough near the end of the last universe could print through the transition onto the earliest light of ours, the cosmic microwave background, the same canvas we keep returning to tonight. Two specific fingerprints have been claimed. The first came in 2010, when Penrose and the Armenian physicist Vahe Gurzadyan reported finding families of concentric circles of unusually low temperature variance in the microwave maps, rings within rings, which they read as the gravitational wave wash of colossal black hole collisions in the aeon before ours, arriving like ripples from storms on a sea that no longer exists. The second claim is stranger and more specific. In 2018, and again with sharpened statistics in 2020, Penrose with Daniel Ann, Christoph Meissner, and Pavel Nurovsky identified what they called Hawking points, roughly 30 anomalously warm spots on the sky, each a few degrees across. Their interpretation is that each spot is the final evaporation of a supermassive black hole from the previous universe, its entire Hawking radiation output, released over spans longer than our universe's age, compressed by the conformal transition into a single hot dot on our infant sky. If they are right, our earliest baby picture contains the death certificates of giants from a cosmos that no longer exists, each one a period at the end of somebody else's story. Now the honest ledger, because a claim this beautiful earns extra scrutiny, not less. Independent groups reanalyzed both claims, and the consensus verdict has been negative. The concentric circles, other teams found, appear at similar rates in simulated skies made of pure standard randomness, once you allow for the freedom involved in searching for any pattern anywhere across a whole sky. The Hawking points met the same objection, the look elsewhere effect, the statistical trap in which a large enough sky, searched hard enough for warm spots, will always provide warm spots. Penrose's collaborators dispute the dismissals, the critics dispute the responses, and the exchange continues in the journals at low volume. There is also a structural objection that troubles cosmologists more than any statistical fight. For the far future to match the Big Bang smoothly, the entropy bookkeeping between aeons has to work out, and Penrose's proposed accounting, in which evaporating black holes quietly erase information, contradicts what most quantum theorists believe about information being indestructible. Conformal cyclic cosmology is, tonight, a minority position held by a great physicist, supported by contested statistics, and carrying an unresolved wound at its theoretical center. The fair summary is not that it is right. The fair summary is that it is the kind of wrong, if it is wrong, that only a handful of living minds are even capable of being. Whatever the sky eventually rules, sit for a moment with the shape of the answer this theory gives to tonight's question. Everything on the far side of our universe's story, on this picture, is another story of the same kind. Universes all the way forward, universes all the way back, each aeon inheriting nothing from its predecessor except the faint scars of its mightiest events, each one living out its trillions of years, unaware that it is a single page. Every triumph and every extinction of the previous aeon has been ironed by the transition into a handful of warm circles on our sky, and everything we are, every city and every name, is headed for the same compression, a few degrees of anomalous warmth in a stranger's dawn. There is grief in that picture if you look for it, and there is also a strange comfort, because in Penrose's universe, nothing is ever the last universe. The cosmos does not end. It turns pages. And a man in his 90s is still at his desk, checking our oldest light for the fingerprints of the book's previous chapter, because if even one Hawking point survives scrutiny, the question of what sits beyond the edge acquires the strangest answer on tonight's list so far. What sits beyond is before. Penrose's beyond, you notice, is reached through time, one universe filing in after another, in single file, sharing the same space, like tenants sharing a room across the centuries. But the reigning theory of our universe's first instant suggests the beyond is far more crowded than that, and far less orderly. It says that what sits outside our cosmos is neither past nor future, but a sea, an ocean of space that never stopped inflating, in which universes bubble up endlessly like foam in a storm, ours among them, one bubble in an uncountable surf. That sea is number 6. Number 6, a sea of other bubbles. The theory at number 6 is the establishment's own monster, the disturbing possibility that mainstream cosmology built with its own hands and has never been able to send away. It begins with inflation, the theory of the universe's first instant, and to understand why respectable physics ends up manufacturing other universes, you need to see the problem inflation was hired to solve. By the late 1970s, cosmologists knew the Big Bang model worked, and knew it carried two glaring mysteries. The universe is almost perfectly uniform, with opposite sides of our sky glowing at the same temperature to 1 part in 100,000, even though those regions, in the plain Big Bang story, never had time to exchange light and agree on a temperature. And the universe is geometrically flat, balanced on the knife's edge we discussed at number 10, a condition that expansion should have wrecked within moments unless the start was tuned to absurd precision. Something in the first instant, it seemed, had smoothed and flattened everything at once, and standard physics had no candidate. In 1981, a young particle physicist named Alan Guth proposed the candidate. Suppose that for a fraction of a second after its birth, far less than a trillionth of a second, the universe was gripped by a state of false vacuum energy that made space itself expand exponentially, doubling in size again and again, dozens of doublings before the state decayed. A patch smaller than a proton would have been stretched to something the size of a grapefruit or far beyond, and the stretching does both needed jobs at a stroke. It irons out any initial lumpiness, explaining the uniform sky, and it flattens geometry the way inflating a balloon to the size of the Earth makes any patch of its surface look flat. Guth called it inflation, borrowing the word from economics with a physicist's dry humor. Over the following decades, the theory matured, made quantitative predictions about the precise pattern of ripples the stretched quantum jitters should have printed on the cosmic microwave background, and watched satellite after satellite, COBE, then WMAP, then Planck, confirm that pattern in exquisite detail. Inflation is, tonight, the reigning account of our beginning, taught in every graduate program on Earth. And it comes with a consequence its own architects did not order. Almost immediately after Guth's proposal, physicists studying how inflation ends discovered that, in generic versions of the theory, it does not end. It only ends in places. Inflation is driven by a field, and quantum mechanics guarantees that the field decays randomly, here sooner, there later. Wherever it decays, inflation stops. The pent-up energy floods into particles and radiation, and a hot Big Bang begins. That is what our Big Bang was, on this account, the local end of inflation, the moment our patch of space stopped stretching and started burning. But the regions where the field has not yet decayed keep inflating, and here is the trap. They inflate so fast that they generate new volume more quickly than decay can consume it. Alexander Vilenkin worked through the logic in 1983, and André Linde generalized it in 1986, and the conclusion has never been dislodged. Once inflation starts, somewhere, it continues forever, an eternally inflating sea of raw, stretching space, punctuated endlessly by bubbles where it locally dies and universes locally begin. Ours is one bubble. The theory that explains our sky's uniformity predicts as standard output an infinity of other skies. Notice what kind of beyond this places outside our edge. Beyond the horizon, past the more of the same territory of number 10, this picture eventually reaches the wall of our bubble, the boundary where our Big Bang happened, and past that wall lies not more universe but the sea itself, space still gripped by inflation, still doubling on timescales so short that a trillionth of a second is an eternity, still spawning new bubbles without end. The sea between bubbles stretches faster than light can cross it, so the bubbles almost never meet, each one sealed behind expansion the way ships in a storm are sealed behind distance, each one a complete cosmos to whoever lives inside. Cosmologists call it eternal inflation, and the resulting ensemble is the bubble multiverse, and it bears repeating that nothing exotic was purchased to get here. Take the standard theory of our own origin, run it forward honestly, and this is what falls out. The picture sharpens and darkens when string theory joins it. String theory, physics' leading attempt at a final unified description of nature, turns out not to specify a single form for empty space. Instead, its equations permit an enormous landscape of possible vacuum states, distinguished by how the theory's extra dimensions fold and how its fields settle, and the standard counting estimate, popularized by the Stanford physicist Leonard Susskind in 2003, runs to around 10 to the power of 500 distinct possibilities. Each vacuum state is a different physics. Different particle masses, different force strengths, different constants, in some cases different numbers of usable dimensions. On its own, the landscape is just a catalogue of hypothetical worlds. But eternal inflation is a mechanism that never stops nucleating bubbles, and each new bubble can settle into a different valley of the landscape. Combine the two, and you get the full proposal in its mature form. The multiverse is not merely many universes. It is many universes running many different laws, the catalogue printed in full, every edition published somewhere, forever. Sit with what that does to the word fundamental. Every constant your existence leans on, the mass of the electron that sets the size of atoms, the strength of the nuclear force that lets stars burn for billions of years instead of instants, the feeble but non-zero cosmological constant that allowed galaxies to form before expansion swept matter apart, all of it becomes, on this theory, local weather. Not law, but climate. Our universe's physics would be one valley's arrangement, no more inevitable than the arrangement of mountains outside a particular town. In bubbles beyond ours, electrons outweigh protons, and chemistry never happens. In others, the vacuum energy is so large that space shreds any structure before a single star can light. The disturbing part is not that those failed worlds exist. The disturbing part is the demotion, the reduction of every law we have ever measured to a zip code. The landscape multiverse would deserve a place on this list as pure speculation, but it earned its rank with one concrete achievement, and the achievement is the reason many physicists tolerate it through gritted teeth. In 1987, the Nobel laureate Steven Weinberg confronted the worst numerical embarrassment in physics, the cosmological constant, the energy of empty space. Straightforward quantum theory estimates that energy at a value roughly 10 to the power of 120 times larger than what the universe displays, the most spectacularly failed prediction in the history of science. Weinberg asked a different question. Suppose the constant varies across a multiverse, and observers can only find themselves in universes gentle enough to grow galaxies. Then the value we measure should not be zero, but small and non-zero, just below the threshold that would have prevented our existence. A decade later, in 1998, the supernova surveys found dark energy, a small non-zero cosmological constant, in the general territory Weinberg's reasoning had indicated. It remains the multiverse's one quiet, unnerving success, a correct prediction pulled from the assumption that our universe is a survivorship artifact, one legible line in a library of static. You should hear the objection too, because it is serious and it has teeth. A theory that explains our constants by invoking unobservable universes has stepped to the edge of what science means, and some physicists say over the edge. The other bubbles lie beyond every horizon we will ever have, forever. Not as a practical limitation, but by the structure of the theory itself. No instrument improves its way past an eternally inflating sea. Critics, including some of inflation's own founders, most vocally Paul Steinhardt, argue that a framework flexible enough to produce every possible outcome somewhere forfeits the ability to be tested by any outcome here, and that eternal inflation's infinities break the machinery of prediction entirely, the measure problem again, now promoted from a technical wound to a philosophical one. Defenders answer that we do not get to vote on the universe's architecture, that the theory earning its keep inside our bubble is evidence enough for what it says about the outside. That argument, over whether the multiverse is physics' greatest inference or its most elegant surrender, is being conducted right now, in seminar rooms on this planet, unresolved. Alan Guth, whose modest fix for two cosmological puzzles set all of this in motion, eventually summarized the situation in a sentence physicists quote with a mixture of delight and resignation. In an eternally inflating universe, anything that can happen will happen, and it will happen an infinite number of times. He meant it as a technical statement about probability, and it doubles as the theory's confession. A framework in which everything occurs infinitely often has a hard time telling you why you are seeing this rather than that, and the difficulty is not rhetorical. It has a name, the measure problem, and it produces genuine absurdities when handled carelessly. Count observers one natural-seeming way, and eternal inflation predicts we should be among the very youngest universes in existence, since new bubbles vastly outnumber old ones at every instant, a bias so extreme it suggests our cosmos should be far younger than it is. Count another way, and different nonsense follows. The infinities can be tamed on paper by cut-off schemes, but the answers change depending on the scheme, and no principle yet chooses among them. Some of the sharpest people in cosmology have spent 20 years on this accounting problem, because until it is solved, a theory containing everything struggles to predict anything, and its defenders know that better than its critics do. Linde, for his part, embraced the picture whole, describing the multiverse he had helped derive as a self-reproducing fractal, universes budding from universes without beginning or end. Inflation, not as an event our cosmos experienced, but as the permanent condition of existence, with big bangs as local weather inside it. He liked to point out that the theory quietly dissolves the oldest question of all, what came before the beginning, by demoting our beginning to one bubble's opening sentence in a book with no first page. Whether that dissolution is profound or merely convenient is, like everything else here, disputed. But notice how the two moods of the same mathematics stare at each other. To Linde, eternal inflation is fecundity, existence too creative to happen only once. To its critics, it is bookkeeping gone feral, infinity eating the theory's predictive power from the inside. Both descriptions fit the same equations, and the equations, indifferent to mood, keep offering the same picture of what sits past our bubble's wall: more sea, more storms, more bubbles, without end and without mercy for the concept of elsewhere. There is, however, one loophole in the multiverse's perfect seclusion, one circumstance under which another universe could touch ours, and astronomers have genuinely looked for it. Bubbles nucleate at random, and while the inflating sea usually carries them apart faster than they grow, two bubbles born close enough together can collide before expansion separates them. The collision would not be an apocalypse for either party, at least not necessarily. Calculations suggest a glancing impact early in our bubble's history would have compressed one patch of our infant cosmos, and the compression would survive today as a disk on the sky, a circular region of the cosmic microwave background, very slightly warmer or cooler than it should be, with a distinctive profile no ordinary fluctuation would mimic. It would be a bruise, the oldest injury in existence, the place where, before our universe had formed a single atom, it was struck by a neighboring one. Picture the event itself, because nothing else on tonight's list offers an image quite like it. You are floating, impossibly, in the inflating sea, where space doubles beneath you faster than thought. Nearby, two bubbles have formed, two universes, each swelling at nearly the speed of light, each containing its own infant Big Bang cooling toward its own future of stars. From outside, they are perfect, silent spheres, growing. They approach one another without malice, without awareness, the way weather approaches weather, and where they meet there is no sound, because there is nothing to carry sound, only a plane of contact where two different vacuums negotiate their difference in an instant of unimaginable energy. Ripples of that negotiation spread backward into each bubble, printing through each one's newborn plasma. And then the sea's expansion tears the two apart forever, two wounded universes receding from one another eternally, each carrying on its sky a fading circular scar, each scar the only proof, for the rest of either cosmos's history, that the other one exists. Teams led by the cosmologists Matthew Johnson and Hiranya Paris ran the search seriously around 2011, developing algorithms to scan the full WMAP sky for collision profiles, one of the first times anyone treated evidence of other universes as an ordinary data analysis problem with error bars. The result was a handful of intriguing candidate patches and no detection that survived statistical scrutiny, and the later, sharper Planck maps did not promote any of them. The multiverse, if it is out there, has left no confirmed fingerprints on our sky. But the search established something quietly important, that the question is not automatically beyond science. A collision early enough and hard enough would have been visible. The universes next door are not hiding. They are merely, so far as we can tell, out of reach or absent, and the sky retains exactly one unexplained mark, large enough to keep the conversation alive. That one mark sits in the southern constellation Eridanus, and it has been bothering cosmologists since 2004, when analysts of the first WMAP maps noticed a region of sky about 5 degrees across, 10 times the width of the full moon, glowing colder than it has any statistical right to. It became known simply as the cold spot, about 70 millionths of a degree below its surroundings, which sounds like nothing until you know that the ordinary ripples of the microwave sky are smaller and shaped differently, and that a dip this size and this profile should be vanishingly unlikely in a standard sky. Explanations divide into 3 families. It could be chance, an outlier the universe was entitled to print somewhere. It could be the shadow of an enormous void, because a great emptiness between us and the background subtly chills light passing through it, while dark energy stretches the void mid-crossing. Or it could be something else. In 2015, the astronomer Istvan Shapudi and his colleagues strengthened the second option by actually finding a candidate, the Eridanus supervoid, one of the largest structures ever identified, a region of depleted galaxies roughly 1.8 billion light-years across, sitting in front of the cold spot like a lens cap. For a while, the mystery looked solved. Then more careful accounting, including work with dark energy survey data in 2022, showed the arithmetic falling short, the void as measured explaining only a fraction of the observed chill under standard physics. The lens cap is real, and it is not enough. Which leaves the third family, and the reason this spot belongs at number 6. The theoretical physicist Laura Mersini-Houghton, whose name has already appeared once tonight, predicted before the fact that our sky should carry at least one anomalous cold region of roughly this character, as the scar of quantum entanglement between our infant universe and a neighbor, an imprint pressed into our bubble at birth by the weight of another. She has maintained for 2 decades that the cold spot is exactly what a young universe looks like, where something else once leaned against it. Most cosmologists do not follow her that far, and the sober ranking of explanations still reads fluke first, void second, other universes a distant third. But it is a measure of where we have arrived, 4 items into this list, that a permanent, unexplained mark on the oldest light in existence, 10 moons wide, has a standing scientific interpretation as a bruise from beyond the edge of the universe, published in journals, neither confirmed nor buried, just waiting there in Eridanus every time we map the sky. Before we leave the sea of bubbles, gather up what this theory quietly does to you, because its human cost is subtler than a scar on the sky. Every law of nature you have ever trusted becomes, on this account, a local bylaw. The equations in every textbook stop being the rules of existence and become the rules of here, the way a nation's laws are laws only inside its borders. And the borders are absolute. The other jurisdictions are not merely far away, they are receding behind a sea that stretches faster than light, so that no journey, no signal, no ingenuity at any point in the infinite future connects your world to theirs. If eternal inflation is true, it is the loneliest true thing anyone has ever proposed, an infinity of company, none of it ever reachable, every universe an island whose ocean grows wider faster than any boat could ever sail. Still, notice the one comfort every bubble shares. However different their laws, All of them float in the same 3 dimensions of space we know, blown from the same sea, made of the same kind of room we live in. The theory at number 5 takes even that away. It proposes that our entire universe, sea and all if the sea exists, is a 3-dimensional sheet suspended in a larger space with more directions than we can point to, and that what sits beyond the edge of the universe is not far away at all. It is beside us, closer than a millimeter, in a direction your body does not contain. Number 5. Membranes in higher dimensions. The theory at number 5 requires you to accept, at least for the next few minutes, that the universe may have more directions than you do. Every motion you have ever made decomposes into 3, forward and back, left and right, up and down. 3 numbers locate any object you will ever touch, and nothing in ordinary experience hints at a 4th option. But nothing in physics says experience is the full inventory, and for a century, serious theories have kept proposing that space has extra dimensions, directions as real as the 3 you know, hidden from you not because they are far away, but because you are not built to travel or even to point along them. The idea entered physics in the 1920s when Theodore Kaluza and Oscar Klein showed that adding a single hidden dimension to Einstein's equations caused electromagnetism, the entire theory of light and charge, to fall out of gravity automatically, as though the 2 forces were one force, viewed from inside a space too small to show its full anatomy. The unification was so beautiful that Einstein himself spent years trying to make it work. It did not, quite in its original form. But the lesson never left, that hidden dimensions are not decoration, they are machinery, and physics keeps rediscovering that it wants them. String theory wants them more than anything before it. The framework treats every particle as a tiny vibrating filament, with each vibration pattern appearing to us as a different particle, and its mathematics is brutally specific about the stage required. The equations demand 9 dimensions of space, and when the theorist Edward Witten unified the framework's 5 competing versions in 1995 into what is now called M-theory, the count settled at 10 dimensions of space plus 1 of time, 11 in all. That is not a preference but a consistency requirement. Take it or leave the theory. For decades, the assumed hiding place for the 7 extras was compactification, the idea that they are curled into loops so small, near the Planck scale, that nothing we can build could ever probe them, every point of our seemingly smooth space secretly wearing a microscopic knot of extra directions. Then, in the middle 1990s, string theorists discovered that their theory contains more than strings. The equations require the existence of membranes, extended objects of various dimensions, called branes for short, and branes turn out to have a remarkable property. The open-ended strings whose vibrations make up ordinary matter and light must have their endpoints anchored to a brane. They can slide along it freely, but they cannot leave it, like beads on a wire, like drawings pinned to a page. Out of that mathematical fact came one of the strangest proposals in modern physics, the brane-world. Perhaps our entire universe, every particle of every atom of every galaxy, is the population of a single 3-dimensional brane, a cosmic sheet suspended in a higher dimensional space that physicists call the bulk. Everything you see is confined to the sheet, because seeing itself is confined to the sheet, photons being strings whose feet never leave the page. On this picture, the question of tonight has a literal, spatial answer at last. Beyond the edge of the universe, beyond every edge, in a direction no compass can indicate, lies the bulk, and we cannot look into it for the same reason a figure drawn on paper cannot look up. What lifts the brane-world from mathematics to physics is that it explains a real and ancient embarrassment, the absurd weakness of gravity. You have been told all your life that gravity is mighty, and compared with nothing it is. Compared with the other forces, it is a rounding error. The electromagnetic force between two protons is stronger than their gravitational attraction by a factor of about 10 to the power of 36, a 1 followed by 36 zeros. A toy magnet the size of your thumb, held over a paperclip, defeats the gravitational pull of the entire planet Earth. 6 trillion kilograms of rock and iron, all pulling one way, outmuscled by a trinket. Physics calls this the hierarchy problem, and it has resisted every conventional solution. The brane-world offers an unconventional one. Suppose gravity is not weak. Suppose it only looks weak because it is the one thing that leaks. Matter and light are open strings, pinned to our brain. But gravity, in string theory, is carried by closed loops of string, and closed loops have no endpoints to anchor. Gravity alone can radiate off the page, spreading its influence through the bulk's extra dimensions, and what we measure on the sheet is just the residue that stays. Gravity's weakness, on this theory, is the draft under a door, our one continuous piece of evidence that there is a hallway. Two versions of the idea electrified physics at the close of the 1990s. In 1998, Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali proposed that the extra dimensions could be large, in particle physics terms enormous, up to a millimeter across, and that experiments had simply never checked gravity's behavior at such short range. A year later, Lisa Randall and Raman Sundram showed you do not even need size. A single strongly warped extra dimension does the job, with space-time curved so severely along the hidden direction that gravity concentrates near one brane and thins to a whisper near ours. And the Randall-Sundram construction carried a detail with a long shadow. Their model contains two branes facing each other across the warped gap, two complete three-dimensional universes, separated along the hidden direction by a distance that can be microscopic. Another world, with its own matter and its own physics, could be suspended less than a millimeter from your hand, and no force you can generate, no light you can shine, would ever cross the gap, because everything you are made of is pinned to this page. Only gravity passes between. A shadow galaxy in the neighboring brane could, in principle, tug on ours through the bulk, and some physicists have noted that unseen mass, tugging on visible matter, is precisely the mystery we currently file under dark matter. That identification is speculative, and most dark matter theorists prefer humbler candidates, but the possibility sits in the literature that the missing mass of our universe is the gravity of furniture in the room next door. Branes also gave cosmology a genuinely new creation story. In 2001, Justin Curry, Bert Overath, Paul Steinhardt, and Neil Turok proposed the ekpyrotic universe, named from the Greek for out of fire, in which the Big Bang was a collision, two parallel branes drawn together through the bulk by their mutual attraction until they met, everywhere at once, the impact's energy flooding both sheets as the heat and matter of a newborn cosmos. In the cyclic elaboration Steinhardt and Turok published the following year, the branes rebound, drift apart, and fall together again across spans of perhaps 1 trillion years, bang after bang after bang, each collision wiping the sheets clean and writing new universes on both. On this account, the beginning of our universe was not a beginning at all, but a clap, one strike in an endless applause, and what sits beyond the edge is the other hand. If the effort of imagining an unpointable direction is making your head swim pleasantly, you are in good company, and the classic remedy was written in 1884. The schoolmaster Edwin Abbott published a slim novel called Flatland, about a two-dimensional world of geometric beings who slide about a plane, and about one square in particular who is visited by a sphere from the third dimension. The sphere cannot show itself to the square, not truly. Passing through the plane, it appears as a circle that grows from a point, swells, shrinks, and vanishes, a sequence the square's entire physics cannot explain, because the visitor's home direction is not merely far away, It is absent from the square's world, orthogonal to every path the square can walk. Up, for the square, is not a secret. It is a nonsense syllable. Brane-world physicists assign flatland to their students for a reason, because on the brane hypothesis, we are the square, our 3 dimensions the plane, and the bulk's extra direction stands to us exactly as up stands to a being made of flatness. If something ever visited from the bulk, we would not see it approach, because approach happens along a direction we do not contain. We would see physics misbehave, a closed room entered, a conservation law bruised, a mass appearing and vanishing like the sphere's swelling circle, and we would have no better vocabulary for it than the square had. Which is why the cleanest modern test of the brane-world came not from a collider, but from a collision far away, and it is one of the quiet triumphs of recent astronomy. In 2017, the LIGO and Virgo observatories caught the gravitational waves of 2 neutron stars spiraling together in a galaxy 130 million light-years off, an event catalogued as GW 170817, and seconds later, telescopes caught its flash of light. The pairing was the prize. Light is pinned to our brain. Gravity is the one thing allowed to leak, so if the bulk exists, the gravitational waves should have shed energy into the extra dimensions across those 130 million light-years, arriving measurably dimmer than the light-based distance said they should be. Astronomers ran the comparison, gravitational brightness against luminous distance, and the waves had leaked nothing. Within the measurement's precision, gravity had traveled those 130 million light-years as faithfully as light did, confined to the same 3 dimensions the whole way. The result closed the door on the largest and leakiest versions of the extra-dimensional universe. It did not touch the smaller, warped versions, whose leakage at those wavelengths would be far below detection. The hallway, if it is there, is narrower than the boldest proposals hoped, and gravity keeps its secrets at least out to the reach of our best interferometers. Ideas this consequential get tested, and the tests are among the most delicate measurements humans have ever performed. If the extra dimensions are large, gravity should abandon Newton's inverse square law at short range, its force spreading into the extra room and weakening faster than the law predicts. At the University of Washington, the EOT-WASH group has spent decades checking, using torsion balances, exquisitely suspended pendulums measuring the gravitational pull between test masses brought within fractions of a millimeter of each other. Instruments so sensitive they must account for the gravity of groundwater shifting after rain. Down to separations of about 50 micrometers, the width of a human hair, Newton's law holds without a flicker. Meanwhile, the Large Hadron Collider ran its own campaign, because brane-worlds with accessible extra dimensions predict collision debris that vanishes from our sheet, energy carried into the bulk by escaping gravitons, and even the possibility of microscopic black holes, which large extra dimensions would make far easier to produce. Careful accounting across years of collisions found no missing energy signature beyond the Standard Model's own bookkeeping, and no micro-black holes. None of this kills the brane-world. It corners it, pushing the hidden dimensions smaller and the energy thresholds higher with every null result. The idea remains what it has been for a quarter century, mathematically serious, experimentally homeless. So hold the honest verdict and the honest shiver together. The verdict is that no experiment has ever caught the bulk existing. The shiver is that if it does exist, the geography of tonight's question turns inside out. Every other theory on this list places the beyond out past the last galaxy, at the end of an unthinkable journey through space. The brane-world places it at 0 distance. The bulk would not be beyond the horizon, it would be beyond your skin, orthogonal to every point of the room you are lying in, a direction the universe keeps folded against every inch of you. You would border the outside of the universe the way a sentence borders the margin, everywhere along your length, and a millimeter in the unpointable direction could hold another complete world, its own night skies pinned to its own page, close enough that its galaxies drift past yours like ships in a fog, felt only as gravity, if felt at all. Nothing on the sheet can ever confirm the hallway. But every time you notice how strangely feeble gravity is, a magnet beating a planet, you are looking at the one measurement that has always been whispering that the page is not the whole book. There is one more move available to a universe made of brains, and it is the reason this item sits where it does, instead of lower. A brain is an object inside a larger space, and objects inside larger spaces can fall. The next theory on this list takes that thought to its conclusion. It proposes that our universe is not floating serenely in anything. It proposes that we are inside something specific, something with a boundary we can name, something that formed in a parent universe by the most violent process gravity allows, and that the edge of our cosmos, the subject of this entire night, is the inside surface of an event horizon. Number 4 says we live inside a black hole. Number 4, the inside of a black hole. The theory at number 4 starts with a coincidence that has been sitting in the textbooks for half a century, quietly refusing to go away. Every mass in the universe has a Schwarzschild radius, the size below which, if you compressed that mass, gravity would win completely and the object would become a black hole. For the Earth, that radius is about 9 millimeters, a marble. For the Sun, about 3 kilometers, a small town. The formula is one line long, and nothing stops you from feeding it the largest mass we know, the total mass and energy content of the observable universe. Do the arithmetic honestly, and something uncanny happens. The Schwarzschild radius of the observable universe comes out on the order of 10 to the 26 meters, which is tens of billions of light years, which is to say, roughly the size of the observable universe itself. We live inside a quantity of matter whose natural gravitational boundary is approximately the boundary we actually see. The physicist Roger Penrose pointed this out in the journal Nature in 1972, in a short paper with the unnerving title suggesting the universe as a black hole, and the mathematician Irving Good floated the same thought around the same time. On the numbers alone, our cosmos is consistent with being the interior of an enormous black hole. That could be numerology, an accident of scales. Or it could be the single largest clue in plain sight. To feel what the claim would mean, you need the essential fact about black holes, which is not their density, but their one-way surface. The event horizon of a black hole is not a material skin. It is a boundary in space-time itself, the radius at which escape would require moving faster than light. Matter and light cross it inward without ceremony. An astronaut falling through a large black hole's horizon would notice nothing at the crossing, no jolt, no wall, no sign. But the geometry on the far side is rearranged. Inside the horizon, the direction pointing back out has, in a precise mathematical sense, become a direction in time rather than space. Escaping is no longer difficult. It is meaningless, exactly as meaningless as walking to last Tuesday. Everything inside falls inward, for the same reason you fall toward tomorrow. And now run tonight's question through that geometry. If our universe is the inside of a black hole, then the edge of the universe is an event horizon viewed from within, and the question of what sits beyond it has a concrete answer. Beyond it sits the parent universe, the larger cosmos containing the black hole that contains everything you have ever known. The sky's oldest light, the most distant galaxies, the entire 93 billion light-year sphere of our night, all of it would be furniture inside an object that, from outside, is a dark and silent sphere hanging in somebody else's sky. Standard general relativity, on its own, does not deliver this picture, because standard general relativity insists that everything falling into a black hole ends at a singularity, a point of infinite density where the equations stop meaning anything. Penrose's own theorems, the ones that earned the Nobel Prize we discussed at number 7, prove the singularity is unavoidable, provided the theory holds all the way down. The interior of a black hole, on the textbook account, is not a universe. It is a funnel, ending in mathematical failure. But almost nobody in physics believes the textbook account survives at the center, because infinite density is not a prediction, it is a confession, the theory announcing the limits of its own jurisdiction. Something must intervene at the extreme, and the theory at number 4 is one specific, worked-out proposal for what intervenes, and for what the intervention builds. The proposal comes from Nikodem Poplavsky, a theoretical physicist at the University of New Haven, who has spent more than a decade developing it in a long series of papers beginning around 2010. His starting point is a modification of Einstein's theory that is nearly as old as the theory itself, called Einstein-Cartan gravity, worked out by the mathematician Élie Cartan in the 1920s. Standard general relativity lets space-time curve but not twist. Einstein-Cartan gravity adds the twist, a property called torsion, and couples it to the quantum spin that every elementary particle carries. Under every circumstance we can observe, the addition changes nothing measurable. The torsion effects are far too small, which is why the theory has survived a century as a respectable, untestable alternative. But inside a collapsing star, at densities beyond anything nature shows us elsewhere, the torsion term wakes up. Poplavsky's calculations find that at roughly nuclear densities and beyond, the interaction between torsion and spin generates a repulsion that grows faster than gravity's compression. The collapse does not proceed to a singularity. It stalls, and then it rebounds, violently, like a spring driven past its limit. Physicists call it a big bounce. Here is the marvel, and it is worth slowing down for. The bounce happens inside the event horizon, so the rebounding matter cannot exit into the parent universe. The one-way door forbids it. Instead, the rebound expands into new volume, space-time inflating beyond the horizon's interior in a way general relativity fully permits, the inside of a black hole becoming, in effect, a new region of existence with its own geometry, cut off from the parent forever. The infalling star's matter, crushed, bounced, and reheated, floods the new region as a dense, hot, expanding plasma. Run the description past any cosmologist without labeling it, and they will name it instantly. A hot, dense, rapidly expanding state, cooling as it grows, is a Big Bang. Poplavsky's proposal is exactly this, that the Big Bang was a big bounce, that our universe is the rebounded interior of a black hole that collapsed in a parent cosmos, and that the process is entirely generic. Every black hole, on this account, is a bridge, its interior hosting a daughter universe. The black holes of our own sky, the stellar remnants scattered through the Milky Way, the 4 million solar mass giant at our galaxy's center, each would contain, on the far side of its bounce, a cosmos of its own, growing, cooling, perhaps lighting stars, perhaps evolving astronomers, each of them sealed behind a horizon that from our side is a boundary and from their side is a sky. The picture rearranges every relationship on tonight's list. The beyond stops being a mystery and becomes an ancestry. Our parent universe is not a speculation about strange geometry. It is a place where, on this theory, a heavy star once ran out of fuel and folded, its core passing some threshold on an ordinary afternoon of its cosmos, and everything we are is the echo of that afternoon. The parent's physicists, if it has them, may have recorded the event as a supernova and a new stellar mass black hole in their catalogues, one entry among millions, an object they will model, weigh, and forget. They cannot know. Their instruments end at the horizon that is our container. And the same asymmetry seals us. We can receive from the parent, in principle, whatever fell in after us, but we can send nothing back, not a photon, not a fact. The mail between universes runs one direction, downhill through the horizon, ancestor to descendant, and every letter is delivered by falling. It is worth pausing on what the crossing itself would have been like, because black hole cosmology quietly answers a question the other theories on this list cannot even pose, the question of what it is like to pass beyond an edge. The answer is that it is like nothing, and that nothingness is the whole point. An event horizon is locally invisible. For a stellar mass black hole, the tides at the horizon would tear a traveler apart, but for a giant, a horizon billions of kilometers across, the crossing is gentle, space-time curving so gradually that no experiment performed in a falling laboratory could identify the moment of passage. The matter of the star that made us, on Poplavsky's account, crossed its own horizon the same way, without ceremony, and every particle that has fallen into that black hole since has entered our universe's history just as quietly. There was no gate, no flash, no welcome. If we live inside such an object, then the single most consequential boundary in our existence, the one this entire video is named for, was crossed by our raw material in perfect silence, and the silence is not a mystery. It is what general relativity promises a horizon feels like from the inside of the fall. The theory also collects a small bonus that cosmologists notice with a raised eyebrow. A bounce interior naturally produces a period of extremely rapid early expansion as the rebounded matter inflates into its new volume, which resembles the inflation era that standard cosmology inserts by hand, and Poplavsky has argued his torsion-driven rebound can play inflation's role without requiring a new field invented for the purpose. The claim is contested. The standard inflation community has its own well-tested machinery, and nothing about the bounce version has been shown to match the precision data as thoroughly. But it marks the theory as more than a metaphysical portrait. It is an attempt at a working cosmology, with early universe predictions that live or die against the same microwave sky as everything else tonight, and its author has spent 15 years accepting that risk in public, paper by paper. Set beside the other items on this list, notice how the flavor of the fear changes here. The infinite universe of number 10 diluted you into endless copies. The multiverse of number 6 demoted your laws to local bylaws. Black hole cosmology does neither. It leaves you unique and your laws intact, and instead, it encloses you. The claustrophobia is genealogical, a universe with a ceiling it can never see through, an origin filed in somebody else's records, a family tree ascending through horizon after horizon, with every rung locked from below. People sometimes find this the most disturbing item on the whole list, precisely because nothing about it is exotic. It requires no extra dimensions, no landscape of vacua, no new particles, only general relativity with one old correction term, plus the black holes we already photograph. The machinery of our imprisonment, if it is imprisonment, is hanging in our own sky in plain sight, by the 100 million. A universe that reproduces invites a thought that physics usually leaves to biology, and in 1992, the theorist Lee Smolin followed it all the way. If universes are born from black holes, and if the laws of physics can shift slightly in the passage through each bounce, the way genes shift slightly between generations, then universes inherit with variation, and inheritance with variation under selection is the complete recipe for evolution. Universes whose constants produce many black holes leave many offspring, each carrying a near copy of the fertile settings. Universes tuned to make few or none are lineages that end. Run the selection for enough generations and the population of universes becomes dominated by cosmic genomes optimized for one thing: black hole production. Smolin called the idea cosmological natural selection, and its most unsettling feature is what it does to the old riddle of fine-tuning. Our universe's constants seem eerily well arranged for stars, carbon, and chemistry, and observers have long argued over whether that calls for luck, a designer, or an anthropic lottery across the multiverse. Smolin's answer is colder than any of those. The constants are not tuned for life. They are tuned for making black holes, because making black holes is what gets a universe descendants, and the ingredients that black hole production requires, long-lived stars, heavy elements, efficient cooling in collapsing gas clouds, happen to be the same ingredients life needs. We would be, on this account, a side effect of cosmic fertility, mice living in the walls of a maternity hospital, mistaking its warmth for a welcome. To Smolin's credit, he did something multiverse theories are routinely accused of never doing. He published a prediction that could kill his idea. If our universe's constants are optimized for black hole production, then no small change to them should increase the yield, and one such dial is the maximum possible mass of a neutron star, the threshold beyond which collapsing remnants tip over into black holes. Smolin's reasoning set an approximate ceiling on that threshold, around 2 solar masses, and he stated plainly that discovering much heavier neutron stars would falsify the theory. For 30 years, astronomers have been weighing neutron stars, and the heaviest confirmed examples sit at about 2.1 solar masses, uncomfortably close to the line, but not clearly over it. The theory lives, on probation, one pulsar discovery away from execution, which is more scientific jeopardy than most ideas about other universes ever accept. And unlike nearly everything else on tonight's list, black hole cosmology makes one more claim your telescope can interrogate. A universe born from a bounce inside a rotating black hole, and essentially all real black holes rotate, should inherit a whisper of its parent's spin. The newborn cosmos would carry a preferred axis, a faint tendency written into everything that forms inside it, and billions of years later, the galaxies condensing from its gas should still remember their rotations distributed not 50-50, but with a slight excess spinning one way. A perfectly standard universe, born with no direction preferred, should show no such excess at all. Which means the question of whether we live inside a black hole reduces, in part, to an audit. Count spiral galaxies. Note which way each one turns. See whether the universe keeps its books balanced, or whether, hiding in the ledger of a billion rotations, there is a thumbprint. In 2025, that audit produced a result strange enough to make international news. Leon Shamir, a computer scientist at Kansas State University, who has spent years building software that classifies galaxy rotations automatically, applied his methods to images from the James Webb Space Telescope's deepest survey, the JAST Advanced Deep Extragalactic Survey, called JADES, a field containing some of the most distant galaxies ever photographed. Of the 263 spiral galaxies in the sample clear enough to classify, a random universe should have split them close to evenly. Instead, 158 rotated clockwise and 105 rotated counterclockwise, roughly 2/3 turning opposite to the Milky Way's own spin, an asymmetry unlikely to be a simple coin flip accident in a sample that size. Shamir himself, publishing in the monthly notices of the Royal Astronomical Society, laid out 2 explanations side by side. The dramatic one is that the universe was born rotating, exactly the inheritance black hole cosmology predicts, a cosmos still carrying the angular momentum of the collapsed star that made it. It is one of the few moments in this entire video where a theory about what sits beyond the edge of the universe connects to a measurement made with an actual instrument on actual galaxies within the last few years. The sober explanation deserves equal time, and Shamir gives it himself. We observe the universe from inside a rotating galaxy, and our own motion can bias what we detect. Galaxies spinning against the Milky Way's rotation are slightly brightened by the Doppler physics of our moving viewpoint, potentially making them easier to identify, an observational thumb on the scale rather than a cosmic one. If that mundane reading is right, the asymmetry is telling us something modest about measurement from a moving platform, though even the modest reading has consequences, since it would mean galaxy surveys across all of astronomy need recalibrating for our own spin. The larger context urges caution too. 263 galaxies is a vanishingly small sample of the estimated 2 trillion out there. Earlier and larger surveys of galaxy spins have disagreed with one another for years, some finding small asymmetries, others finding none, and no independent team has yet confirmed a rotation signature strong enough to settle anything. The verdict tonight is honestly unsettled. The universe has not been shown to spin. It has merely declined, so far, to prove that it does not. Step back and weigh what this theory does to the ordinary night sky. If Poplavsky is right, every black hole astronomers have catalogued, the X-ray binaries, the gravitational wave mergers, the sleeping giants at the centers of galaxies, is a sealed maternity ward, an entire cosmos in progress behind a door with no handle on our side. The Milky Way alone is estimated to contain on the order of 100 million stellar mass black holes, which would make our one galaxy the ancestor of 100 million universes, each potentially growing its own galaxies, its own black holes, its own descendants, a family tree branching beyond all counting. And our own edge, the horizon this entire video keeps circling, becomes a birth certificate, the inside surface of the event that made us. Somewhere beyond it on this theory, there is a sky in which our whole universe is one dark point among millions, weighed and catalogued by astronomers who will never learn its contents, and who may themselves live inside a point in a catalogue one level further up, wards within wards, skies within skies, with no top floor anyone has ever demonstrated. A horizon that seals a universe from its parent raises one more possibility, and it is the strangest pivot on tonight's list. Every theory so far has treated the edge as a boundary between here and elsewhere, a line with our reality on this side and something else on that side. The theory at number 3 dissolves the distinction entirely. It proposes that the boundary is not a wall in front of the real thing. It proposes that the boundary is the real thing, that the two-dimensional surface wrapping a region can carry, complete and exact, everything the region contains, and that our three-dimensional world, depth and distance and the space behind your closed eyes, may be the projection of a script written at the edge. Number 3 is the holographic principle. Number 3, the surface of a hologram. The theory at number 3 began with a graduate student refusing to be talked out of an idea, and the refusal is worth telling properly, because everything that follows tonight descends from it. In 1972, Jacob Bekenstein was a doctoral student at Princeton under John Wheeler, the physicist who had given black holes their name. Wheeler posed his student a teasing puzzle. Take a cup of hot tea, an object full of entropy, of thermal disorder, and pour it into a black hole. The tea is gone. Its entropy is gone from every ledger in the visible universe. Has the second law of thermodynamics, the rule that total disorder never decreases, the most secure law in all of physics, just been repealed by a drain? The safe answer was that the law simply does not apply to black holes. Bekenstein gave the unsafe answer. He proposed that the black hole itself must have entropy, that swallowing the tea increases that entropy, and that the books balance after all. And he went further, because the mathematics pointed somewhere specific. When a black hole swallows anything, its event horizon grows. Bekenstein proposed that the horizon's surface area is the entropy, that the measure of everything ever lost into the whole is written in some unreadable accounting on the size of its boundary. The proposal was received badly, and the person it offended most consequentially was Stephen Hawking. Entropy implies temperature, Temperature implies radiation, and a black hole, by definition, radiates nothing. So Bekenstein's idea seemed not merely wrong but self-contradictory, and Hawking set out to prove it so. In 1974, he finished the calculation that was meant to be the refutation, treating quantum fields with full care in the curved spacetime at a horizon, and found the opposite. Black holes do radiate. They have a temperature and an entropy, and the entropy is exactly proportional to the horizon's area, precisely as the graduate student had insisted. Hawking radiation became the most celebrated theoretical result of its era, and Hawking, to his lasting credit, spent the rest of his life building on the young man's idea he had tried to demolish. Bekenstein, a quiet and devout man who died in 2015, lived to see the formula for black hole entropy, with his name on it beside Hawking's, proposed by some as the one equation deserving engraving on physics' tombstone if the field ever ended. It carries a message no one ordered. The information content of a region of space is measured not by its volume, but by the area of the surface that wraps it. Stop and let that land, because it is the strangest fact tonight that is not a speculation, but a theorem-grade result of standard physics. Ask how much information a region of space can possibly contain, how many bits you could store there before the storage itself collapses into a black hole, and the answer does not scale with the region's volume, the measure of its inside. It scales with its surface area, the measure of its wrapping. Double a room's radius and its volume grows eightfold, but its information ceiling grows only fourfold. Space, in other words, holds less than it appears to, as though the interior were not the fundamental container, as though the real storage were the walls. Nothing in daily life prepares you for that arithmetic. It is as if you discovered that every book's contents were fixed not by its pages but by its cover, and the pages were somehow a rendering of the cover's fine print. Two of the deepest thinkers in physics decided to take the arithmetic at face value. In 1993, Gerard Hooft, who would later win the Nobel Prize for other work, proposed what he called dimensional reduction, the idea that the surface scaling is not an oddity of black holes, but a disclosure about nature, that the fundamental description of any region of the universe genuinely lives on its boundary, with one dimension fewer than the world we experience. 2 years later, Leonard Susskind developed the proposal into what he plainly titled the holographic principle, borrowing the metaphor that has carried it ever since. A hologram on a credit card is a two-dimensional film that, held to the light, produces a fully three-dimensional image, depth conjured from flatness by the encoding of interference patterns. The holographic principle proposes that our three dimensions of space stand in exactly that relationship to a two-dimensional description we cannot see, that depth itself, the third dimension, the space behind and in front of every object you know, is not fundamental but emergent, reconstructed from information whose native home is a surface. For a few years, the principle was a philosophy with excellent credentials. Then, in 1997, a young Argentine physicist named Juan Maldacena made it mathematics. Working on the relationship between string theory and quantum field theory, Maldacena discovered an exact correspondence between two apparently different worlds. On one side, a universe with gravity, strings, and black holes, a five-dimensional curved spacetime of the kind called anti-de Sitter space. On the other side, a quantum theory of particles with no gravity at all, living on that universe's four-dimensional boundary. The correspondence is a dictionary. Every object, every event, every process in the gravitating interior translates exactly into an object, event, or process in the boundary theory, and vice versa, nothing lost in either direction. A black hole forming and evaporating in the interior translates into an ordinary, if complicated, heating and cooling of particles on the boundary. The interior and the boundary are not two systems that resemble each other. They are the same system, written in two notations, and neither notation is more real than the other. Maldaceno's paper became the most cited in the history of high-energy physics, with tens of thousands of citations, and it converted the holographic principle from a metaphor into the daily working equipment of an entire field, used now to study everything from evaporating black holes to the behavior of exotic superconductors. The honesty this list owes you cuts in both directions here. The proof-of-concept universe in Maldaceno's correspondence is anti-de Sitter space, a space-time curved the opposite way from ours, a cosmos wrapped in a boundary like a snow globe in glass, where our universe, with its accelerating expansion, has no such convenient wall. No one has yet constructed the exact holographic dictionary for the universe we actually live in, and it remains possible that none exists, that holography is a property of the snow globe and not of the open sky. But the direction of travel in fundamental physics for a quarter century has been toward taking the principle as general, a constraint any final theory must respect, and there have even been attempts to test its cosmological versions against data. In 2017, the physicist Nyayesh Afshordi and colleagues showed that a class of holographic early universe models fits the measured pattern of the cosmic microwave background about as well as standard inflation does, not better, but as well, which is a remarkable sentence to be able to write about a proposal this strange. And at Fermilab outside Chicago, the physicist Craig Hogan built an instrument called the holometer, twin laser interferometers hunting for a specific holographic jitter in space itself, a pixelation of position at the finest scales. In 2015, it reported silence, ruling out Hogan's particular version and leaving the broader principle untouched, the way a null result at one shore does not drain the ocean. Between Bekenstein's proposal and Maldaceno's proof, there was a war, and the war is how the principle earned its seriousness. Hawking's radiation carried a paradox in its pocket. The radiation leaking from a black hole, in his calculation, is perfectly thermal, featureless, carrying no imprint of whatever fell in, so when the hole finishes evaporating, the information of everything it ever swallowed appears to be gone from the universe, not hidden, not scrambled, but erased. Quantum mechanics forbids erasure absolutely. Its equations run backward as reliably as forward, and so the two pillars of 20th century physics were in open contradiction at the site of a black hole's death. Hawking bet on gravity, arguing for decades that information really is destroyed, and that quantum mechanics must yield. Susskind, alongside Hooft, bet on quantum mechanics and fought what he later titled, in a memoir, The Black Hole War. Holography was the weapon that ended it. If the interior of a black hole is fully encoded on its horizon, then nothing that falls in is ever truly inside and gone. The information remains available at the surface, and the radiation, read finely enough, carries it back out, scrambled beyond practical recovery, but never erased. Maldaceno's correspondence made the argument nearly airtight for the model universes it covers, since there, a black hole's whole life translates into ordinary quantum physics on the boundary, where information cannot die by construction. In 2004, Hawking conceded, publicly, at a conference in Dublin, settling a famous bet with the physicist John Preskill by handing over an encyclopedia of baseball, information, as he noted with a smile, retrievable at will. The surface had won. Physics' deepest crisis in a generation was resolved by concluding that the boundary keeps the books for the interior, and once that conclusion is accepted for black holes, the question of whether it holds for the universe entire becomes impossible to unask. The numbers involved make the proposal feel less like poetry and more like an audit. Our observable universe has a boundary of sorts, the cosmic horizon, and applying the Bekenstein-Hawking accounting to it yields a total information capacity on the order of 10 to the power of 122 bits, the same colossal figure that kept appearing at number 10, now wearing a different uniform. Every quantum event in the visible cosmos, every particle collision since the Big Bang, every thought every brain will ever have, fits with room to spare inside that ledger, and the ledger's size is set by an area, not a volume. For comparison, all the data humanity has ever produced, every book, photograph, and server farm, is estimated in the tens of zettabytes, roughly 10 to the 23rd bits, which stands to the cosmic ledger as far less than a single atom stands to the whole universe. We are, informationally, a stray pencil mark in one corner of a page whose full text no one inside the page can read. Even the fate of that page has been priced. The horizon of an accelerating universe like ours carries its own entropy and its own faint temperature, and some theorists have spent their careers trying to build the boundary description of a cosmos like this one, where the wall is not a solid frame at the outskirts of a snow globe, but a horizon that every observer carries with them, each of us wrapped in our own informational surface. If they succeed, the last of tonight's geography inverts for good. The edge stops being the place where the universe runs out and becomes the place where the universe is written down, with each of us at the center of our own page, projections of documents that follow us wherever we go and end exactly where our seeing does. To feel the Bekenstein bound as more than an abstraction, run it on something you care about, yourself. A human brain, the densest known concentration of organized information in the universe, stores its memories and itself in the arrangement of roughly 86 billion neurons and their 100 trillion connections, an inventory that information theorists estimate in the broad vicinity of a few petabytes, 10 to the 16th bits or so, give or take generous uncertainty. Now draw a sphere around your head and ask the Bekenstein accounting what that region of space could hold at the absolute physical maximum, and the answer comes out around 10 to the power of 42 bits, 1,000,000 trillion times more than the brain uses. We are nowhere near the ceiling, and that is the point usually missed about holography. The bound is not a constraint anyone bumps into. It is a disclosure about bookkeeping, the fact that the ceiling exists at all, and that it is written on the sphere and not in the volume, is the entire scandal. Nature could have made information scale with space, the way furniture does. Instead, she made it scale with wrapping paper, and 4 decades of physics has failed to make that fact go away or mean less than it seems to. The idea has even begun to reach for the third dimension's throat directly, in a program that grew from Maldaceno's dictionary through the 2000s and 2010s. Physicists studying the correspondence noticed that the amount of quantum entanglement between two halves of the boundary theory computes exactly the area of the surface connecting them through the interior, as though entanglement were not merely correlated with geometry, but generative of it. The physicist Mark van Ramsdonk pressed the logic to its conclusion in a celebrated argument, showing that as you dial the boundary's entanglement down in the mathematics, the interior spacetime literally pinches apart, regions disconnecting from one another like a bridge dismantled cable by cable, and as you restore the entanglement, the bridge rebuilds. Space, in these calculations, behaves as though it were made of quantum correlation, distance itself a measure of how weakly two parts of the boundary's data are entangled. None of this has yet been demonstrated for our own universe. The honest asterisk stands where it stood. But inside the model worlds where physics can check, the third dimension assembles out of information the way a dream assembles out of memory, and the assembled space contains observers who would swear, as we do, that the depth around them could not possibly be anything but fundamental. Now bring the principle home to tonight's question, because it does something to the edge of the universe that no other theory on this list attempts. Every other item treats the edge as a frontier with territory past it, more space, other bubbles, a parent cosmos, and asks what the territory holds. Holography reverses the geography of the question itself. If the deepest description of a region lives on its boundary, then the surface wrapping the cosmos is not the end of the real thing. It is the most real thing, the master copy, and the three-dimensional interior, the galaxies, the distances, the depth of the night sky, is the projection, the rendering, the image the boundaries information throws. Asking what sits beyond the edge of the universe on this picture is like asking what sits behind a cinema screen expecting to find the rest of the movie. There is nothing behind the screen. The movie is not deeper than the screen. The screen is where the movie lives, and the depth you experienced was the encoding, not the architecture. Be precise about what this does and does not claim, because the word hologram invites a misunderstanding the theory does not deserve. Nothing about the holographic principle says you are an illusion. The interior description, the one with 3 dimensions and you in it, is complete, consistent, and true. Your pain and your childhood and the weight of your own hands are exactly as real as physics ever certifies anything to be. The claim is about bookkeeping, about which description is fundamental, and it says the fundamental ledger of everything you are, every particle's state, every synapse's configuration, every memory encoded in the wet circuitry behind your eyes, is written, without remainder, on a 2-dimensional surface at the boundary of your region of the cosmos. There is, tonight, on this theory, a flat and distant document that is you, not a copy of you, not a record of you, but the original of which the person in your bed is the projection. You cannot visit it, because visiting is a thing projections do inside the projection. You cannot read it, because you are a sentence trying to turn and see its own page. The strangeness compounds when you ask what happens to space itself in this accounting. Depth, distance, the whole 3rd dimension, becomes emergent, a construction the boundary information generates, the way the depth in a stereogram emerges from flat patterns when your eyes settle. And ongoing work in the field has pushed one step further, into evidence from the mathematics that space is stitched together by quantum entanglement, that the connectedness of here to there, the very property of the universe having an inside, is woven from correlations in the boundary data, thread by thread. Cut the entanglement, the equations suggest, and space itself falls apart into disconnected patches, the way a movie dissolves into static when the film is scratched. If that program is right, then the universe's interior, the entire subject of astronomy, is something the edge is doing. The beyond does not sit past the boundary. The beyond is a question the boundary's grammar cannot even form, because everything, including the concept of past, including the room you are in, including the drowsy mind now holding this thought, is the boundary, elaborated. The hologram, whatever else it takes, at least preserves. Every bit is kept. The principle is built on the impossibility of information being destroyed, and the surface at the edge of everything forgets nothing. The theory one step down the list preserves nothing. It is the only item tonight that does not merely sit beyond the edge, but may be in transit from it, and of everything in this video, it is the entry physicists themselves joke about most carefully. Number 2 is the possibility that the vacuum of space is a held breath, and that somewhere beyond the horizon it has already been released. Number 2, a bubble already on its way. The theory at number 2 concerns the quietest object in physics, the vacuum, and the possibility that it is lying to us. Empty space, in quantum field theory, is not nothing. It is the ground floor of every field in nature, the setting each field relaxes into when all the particles are removed, and the properties of that ground floor determine everything built above it. The masses of particles, the strengths of forces, the rules of chemistry, all of it is architecture, resting on the vacuum's foundation, and physics has a precise way of asking whether a foundation is sound. Picture a ball resting in a valley among hills. If the valley is the lowest point in the entire landscape, the ball is truly stable, and the vacuum it represents will hold forever. But a ball can also rest in a high valley, a hollow partway up the range, perfectly still, perfectly convincing, and not at the bottom. Physics calls that state a false vacuum. It can persist for eons, supporting its architecture without a tremor, while below it, across a ridge no classical process can cross, there is a deeper valley, a true vacuum, a lower energy arrangement of reality that the universe would prefer. Classically, a ball in a high valley stays there. Quantum mechanically, nothing stays anywhere. Quantum fields fluctuate eternally, and there is a calculable probability, tiny but never zero, that somewhere, at some moment, a small region of the field tunnels through the ridge, straight through the barrier, and finds the deeper valley on the far side. The event is called bubble nucleation. A microscopic pocket of true vacuum appears inside the false one, and its fate is decided by an energy budget, the cost of maintaining the bubble's wall against the reward of the interior's lower energy. Small bubbles collapse and vanish. But past a critical size, the reward wins, and the bubble grows, converting false vacuum to true at its expanding surface, and the growth does not saunter. The energy released at the wall accelerates it, relentlessly, asymptotically toward the speed of light, until the boundary between the old world and the new is sweeping through space essentially as fast as causality allows anything to move. The definitive analysis of this process, including gravity's role in it, was published in 1980 by Sidney Coleman and Frank DeLucia, and it stands among the most quietly influential papers in theoretical physics. Coleman was one of the great minds of his generation, legendary at Harvard for lectures of surgical clarity and a wit his students repeated for decades, and the paper's most famous passage reads like him, beginning as dry analysis and ending somewhere no physics paper had gone. Vacuum decay, they wrote, is the ultimate ecological catastrophe. After the wall passes, not only is life as we know it impossible, but so is the chemistry that could support any life we could imagine, and the constants of nature themselves are reassigned. They noted, with what one can only call gallows precision, that a possible consolation, the thought that the new vacuum might in time grow its own kinds of structures and its own ways of being, is not available either in the worst cases, where the new region's physics permits nothing organized at all. The paper's language has been quoted at physics conferences for 45 years, half as a joke, half as a liturgy, because everyone repeating it knows the calculation underneath is sound. For decades this remained an elegant hypothetical, because no one knew whether our own vacuum was the true floor or a high valley, and there was no way to check. Then the check arrived, from the most expensive scientific instrument ever built. In 2012, the Large Hadron Collider at CERN discovered the Higgs boson, the particle of the field that gives other particles their mass, and measured its mass at about 125 giga-electron-volts. That number, which sounds like a mere catalogue entry, turned out to be a verdict, because the shape of the vacuum's energy landscape, the very question of valleys and ridges, can be computed from the Standard Model's parameters, and the computation is exquisitely sensitive to exactly two of them, the mass of the Higgs and the mass of the top quark, the heaviest particle known. Teams of theorists ran the calculation with full rigor in 2012 and 2013, extrapolating the known laws to the highest energies, and the result has not moved since. With the measured masses, our vacuum is not stable. It is metastable. The Higgs field's current value is not the bottom of the landscape. Far away, at energies enormously beyond anything ever probed, the calculation finds a deeper valley, and our universe, on the face of our best particle physics, is a ball resting in the high hollow, a held breath, a false vacuum that has simply not yet gotten around to failing. The result deserves every qualification it comes with, and it comes with several. The calculation assumes the Standard Model's equations hold unmodified across 16 orders of magnitude of energy where we have no data, a bolder extrapolation than physics has ever confirmed elsewhere, and any new particle or force in that desert could redraw the landscape entirely, possibly into perfect stability. The measured masses also sit strangely close to the boundary line between stable and metastable, so close that some theorists suspect the near criticality itself is the real message, a hint about deeper principles rather than a death sentence. But take the face value, as this list takes every theory's face value, and the situation is this. The laws of nature, as currently measured, imply that the vacuum underneath every atom of you is provisional. Not wrong, not failing, provisional, the way a building's foundation is provisional when the survey says the deeper bedrock lies elsewhere and nothing has slipped yet. And the timescale, mercifully, is the kindest number in this entire video. The expected lifetime of our vacuum, computed carefully in 2018 by physicists at Harvard, comes out around 10 to the power of 139 years, with an uncertainty range whose far end stretches to 10 to the power of 549. The universe's current age, against numbers like that, is not even a rounding error. If the entire history of the cosmos so far were one tick of a clock, the expected wait for vacuum decay would be more ticks than there are atoms in a billion universes. Probabilistically, no region anywhere near us should nucleate a bubble before every star has died, every black hole has evaporated, and every era we discussed at number 7 has come and gone many times over. The fear, such as it is, was never really about the odds. It is about the shape of the thing the odds describe, because low probability per year, multiplied by infinite space and endless time, stops being a reassurance and becomes a schedule. Nature, it turns out, has already run the safety trial, and the result is genuinely comforting. In 1983, the physicists Piet Hut and Martin Rees addressed a worry that surfaces every time humanity builds a bigger particle collider, the fear that some experiment might accidentally tip the vacuum over its ridge. Their answer was to point at the sky. Cosmic rays, particles accelerated by exploding stars and feeding black holes, strike our atmosphere and every other body in the universe continuously, and the most energetic of them collide at energies millions of times beyond anything any human machine has ever achieved or will for centuries. Those collisions have been happening everywhere for 13.8 billion years, countless quadrillions of natural experiments at stakes no collider approaches, and the universe is still here. Whatever the vacuum's ultimate verdict, nothing humanity does in a tunnel under Geneva is going to hurry it. The danger, if the word even applies, was never from us. It was always from the arithmetic of elsewhere. Because here is the property that earns false vacuum decay its place at number 2 on a list about what sits beyond the edge. Bubble nucleation is a local, random event, equally probable in every cubic centimeter of false vacuum, and there are unimaginably more cubic centimeters beyond our horizon than inside it. If the universe is infinite, or even merely enormous, then somewhere beyond the edge, the odds stop being odds. Somewhere, arguably inevitably, a bubble has already formed. As you lie there tonight, on this theory's plain reading, there are regions of existence where the vacuum has already failed, where the deeper valley has already been found, and where a wall of new physics is expanding outward at essentially the speed of light, erasing worlds that never saw it coming. This is not a monster beyond the wall. It is the wall in motion, and the question of what sits beyond the edge of the universe acquires, at number 2, its only answer that could ever be described as incoming. And no warning is possible, even in principle. The bubble wall travels so close behind its own light that the news of its approach and the thing itself arrive effectively together. There is no astronomy of vacuum decay, no distant glow to catch, no signal that outruns it, no sky survey that could buy the world an afternoon. A civilization of unlimited patience and genius, watching with perfect instruments, sees nothing until the nothing is here. The physicists who write about this are always careful to add the strange mercy inside that fact. The wall's arrival would also be the fastest thing that ever happened to us. Nerve impulses crawl along your body at 100 meters per second and change. The wall arrives at 300 million meters per second. The ratio between them is millions to 1, which means the interval between the wall touching your skin and the wall having finished is shorter by orders of magnitude than the time your nervous system needs to register that anything is occurring. There would be no flash, no heat, no fear, no noticing. Every account of vacuum decay in the literature agrees on this single point of bedside manner. It is the one apocalypse that cannot hurt. What actually changes when the wall passes is worth stating carefully, because the phrase new physics can sound abstract and the reality is intimate. The masses of the fundamental particles are not properties the particles carry privately. They are set by the Higgs field, by how deeply that field settles into its valley, and everything in chemistry is downstream of the settings. The size of an atom is fixed by the electron's mass. The stability of a nucleus depends on the delicate margins between quark masses. The reason your body holds together, the reason water dissolves what it dissolves, the reason DNA's rungs pair and part at exactly the temperatures life needs, all of it is the fine print of the current vacuum. Inside a decayed region, the Higgs field sits at a profoundly different value. The particle masses are reassigned wholesale, and the periodic table is not amended but repealed. There would be no corroded version of our world on the far side of the wall, no ruins, no chemistry limping along under new management. Matter as a category, the whole idea of stable, structured stuff, is a local ordinance of the false vacuum, and the true vacuum, in the calculations we can do, does not reenact it. What the bubble contains, most likely, is a permanent, structureless, quiet, gravity and radiation, and the long patience of a space that no longer builds anything. There is a strange footnote here, and it connects this item to the sea of bubbles at number 6 in a way physicists find almost poetic. Coleman and DeLucia showed that the interior of a nucleated bubble, described in its own coordinates, is not a shrinking pocket, but an open, infinite universe of its own, born from the tunneling event the way our cosmos may have been born from the end of inflation. Some cosmologists have taken the resonance seriously, because eternal inflation's bubble universes and vacuum decay's bubbles of ruin are, mathematically, the same species of object viewed in different moods. Our own Big Bang, in some corners of the theory, may itself have been a vacuum decay event inside a higher, falser vacuum, which would mean the catastrophe this item fears has already happened once, and we are what the inside of the catastrophe looks like, 14 billion years into its settling. The wall that would end our world and the event that began it might be the same kind of moment, wearing different directions in time. The idea has also had its brushes with public panic, and the record there says more about us than about the vacuum. When the relativistic heavy ion collider was preparing to switch on in New York at the end of the 1990s, newspapers carried claims that it might create a planet-swallowing calamity, and a decade later, the Large Hadron Collider attracted actual lawsuits filed in real courts, seeking to halt its activation on the grounds that it might destroy the Earth, with vacuum decay on the list of alleged mechanisms. The physics community's response was the Hutt and Rees argument we have already met. Formalized in safety reviews, the universe has been running these collisions at incomparably higher energies for its entire history, on every rock and every star, and the persistence of the sky is the trial data. The courts dismissed the suits. The colliders ran. Nothing happened, exactly as the cosmic rays had promised. But the episode left a lasting image of the strange psychological position this theory occupies, a doomsday too slow to fear on any human timescale, too total to forget once heard, and too well-behaved mathematically to dismiss as fiction. It is the physics equivalent of learning as a child, that the sun will one day swallow the earth, information that changes nothing about tomorrow and something, permanently, about you. With the mechanism, the timescale, and the safety record in hand, we have earned the right to look at the thing itself, once, in the only register this channel allows. Let the scenario play once, gently, so that we can set it down afterward and look at what protects us. It is an ordinary evening somewhere on Earth, this one, if you like. A kettle is coming to temperature in a kitchen. Someone is reading in the next room, one leg folded under the other, and through the window the first stars are sorting themselves out of the blue. Far away, past the last galaxy any telescope will ever image, the wall has been traveling for 2 billion years. It crosses the distance of a galaxy in 100,000 years, the gap between galaxies in a few million, and it makes no light and casts no shadow, because light is part of what it is replacing. The kettle begins its low murmur. The reader turns a page, and the sentence on the new page begins, the way sentences do, with every intention of ending. There is no sound. There is no brightness. The wall arrives, and the constants that hold the ink to the page to the hand to its history, are reassigned mid-letter, and the sentence does not finish, anywhere, ever. Nothing in the kitchen objects. Objecting takes milliseconds, and the world had less. What follows the wall is not wreckage. Wreckage is made of atoms, and atoms were a custom of the old vacuum. What follows is simply the next physics, calm, complete, and unacquainted with kettles. Now exhale, and let the same physics that staged that scene dismantle it, because this is the part of number 2 that the frightening summaries always omit. That wall cannot reach this kitchen, not from where we placed it, and the reason is the discovery that has shadowed this whole video. The expansion of the universe is accelerating, and space between distant points grows faster than light can cross it. We met the consequence hours ago as the cosmic event horizon, the boundary 16 to 18 billion light-years out, past which no signal sent today can ever arrive here. A vacuum decay bubble, for all its speed, is still a signal, still bound by causality, still crossing space while space itself pours in ahead of it, faster than it can swim. Any bubble that nucleates beyond our event horizon is not merely far away. It is disqualified, permanently, its wall gaining ground on us more slowly than the road lengthens, forever. Do you remember the postcard that can never arrive, the image we used for the mail of the deep universe? Here is that image, turned inside out and handed back as a shield. The one-way isolation that makes the cosmos beyond the horizon unknowable, the loneliness we have been mourning all night, is also the quarantine that makes its catastrophes powerless. Almost everything that exists is already out of range of any single bubble, and almost every possible bubble is already out of range of us. So the honest bottom line of number 2 runs like this. Our best particle physics says the vacuum is metastable, and the calculation may simply be missing new physics that stabilizes everything. If decay is possible, the expected timescales dwarf every other future event in this video. If a bubble forms anyway, it can only ever claim the finite region inside its own causal reach, and an accelerating universe keeps shrinking what any one bubble can own. What the theory truly costs you is not safety. Statistically, you have never been safer from anything. It costs you the permanence of the flaw. The laws of physics on this account stop being a deed and become a lease, terms subject to revision by a landlord who has never once spoken, and the silence beyond the edge of the universe becomes, on your worst nights, the sound of the revision not arriving. And yet, notice what even this theory concedes, and every theory tonight has conceded it in its own way. The bubble, the sea, the parent cosmos, the previous eon, all of them still furnish the beyond with something. Every fear we have entertained for nearly 3 hours has been, at bottom, a fear of what the outside contains. The final item on this list is what happens when physics stops furnishing, and it is stranger than anything a bubble could deliver. Number 1 proposes that the outside contains nothing, because there is no outside to contain it. Number 1, nothing at all. We arrive at number 1, and it is only fair to warn you what kind of answer this is. Every theory tonight has been a furnishing of the dark. We have filled the beyond with copies and mirrors, with currents and corpses, with seas of bubbles and stacks of pages and parents, and walls in motion, and whatever else those pictures did, they all agreed to the premise of the question. Something sits beyond the edge. The only argument was over what. Number 1 is the answer most working cosmologists would actually give you, delivered gently at the end of a long dinner, when the speculation has burned off and someone finally asks what they really think. The answer is that nothing sits beyond the edge of the universe. Not empty space. Not blackness. Not a void waiting to be filled. Nothing in the strict and dizzying sense that there is no beyond for anything to sit in, and the question we have spent 3 hours asking may be a sentence-shaped thing that does not, in the end, refer to anything at all. The path to that conclusion begins with the most common misunderstanding in all of cosmology, and it is worth dismantling with some care, because the misunderstanding is doing the emotional work behind tonight's entire premise. The universe is expanding, and the word expansion drags an image along with it. Things that expand, in every experience you have ever had, expand into something. The balloon inflates into the room. The ripple spreads across the pond. So when astronomy reports that all the distant galaxies are receding, that space itself is stretching, the mind helplessly supplies a room for the stretching to happen in, some larger emptiness that the universe's frontier is advancing through, and with the room comes an edge, the surface where the advance has gotten to. That image, natural as breathing, is wrong in its very grammar. The expansion of the universe is not motion outward through anything. It is an internal stretching, a growth in the distances themselves. Take any 2 distant galaxies, and the number of kilometers between them increases with time, not because either one travels, but because kilometers are being added to the interval, everywhere all at once, the way new words lengthen a text from within. The galaxies are not fleeing through space toward a frontier. They are standing nearly still while the space between them breathes. Even the balloon, handled honestly, teaches the right lesson. When cosmologists offer that analogy, the universe is not the balloon's interior, it is the balloon's surface, the 2-dimensional rubber skin, with every galaxy a dot drawn on it. Inflate the balloon and every dot recedes from every other, distances growing uniformly, no dot central, no dot at an edge, which is precisely our sky. But ask the analogy tonight's question. Ask what the surface is expanding into, and notice what you are doing. You are stepping off the rubber, into the surrounding room, and using the room to make sense of the growth. Here is the point on which the entire finale turns. The mathematics of the expanding universe needs no room. General relativity describes the stretching of the surface from within the surface, completely, with nothing left over, and when the description is complete from within, the room is not a hidden part of the story. It is a habit of the analogy, scaffolding your imagination brought to the job, and the universe never asked for it. The mathematics that makes this possible has a birthday, and it is one of the quiet hinges of intellectual history. Until the 19th century, geometry was the study of figures inside a larger space, curves on a page, solids in a room, everything curved relative to a flat container that did the measuring. Then Carl Friedrich Gauss, surveying and calculating in the 1820s, proved a result he found so remarkable he named it the Theorema Egregium, the outstanding theorem. The curvature of a surface, Gauss showed, can be determined entirely from measurements made within the surface, from distances and angles alone, without ever consulting the container. A being confined to a sphere's skin, with no concept of the third dimension, could still discover its world was curved, by drawing a large enough triangle and finding its angles total more than 180 degrees. His student Bernhard Riemann then rebuilt geometry from the inside out, defining space by its internal distance rules alone, no container required, any number of dimensions, curved or flat, finite or infinite, each a complete world unto itself. When Einstein needed a language for gravity a half-century later, this was the language, and the point cannot be overstated. General relativity, the theory this entire video has been living inside, describes the universe intrinsically. Its equations mention no outside, use no outside, and would not know what to do with an outside if one were supplied. The cosmos of modern physics is not a thing in a place. It is the place. With intrinsic geometry in hand, the two possible universes both lose their edges, each in its own way. If space is infinite, the flat reading of the data we met at number 10, then there is no boundary for the plainest reason imaginable. The galaxies simply never stop, and the question of what lies beyond them is empty because there is no beyond, only more. But the finite case, the one that has always seemed to demand an edge, loses its edge too, and this is Riemann's gift to tonight. A finite universe, in general relativity, is finite the way the Earth's surface is finite, closed upon itself, a definite total size with no rim anywhere. Ask what is beyond the surface of the Earth while confined to walking on it, and the answer is nowhere on the map. Every step in every direction lands on more Earth, and the surface's total area is finite all the same. A closed universe does in 3 dimensions exactly what the Earth's surface does in 2. Sail your ship of number 9 as far as you like, in any direction, for any span of time, and you meet more universe, always, without the total being infinite, without any wall being dodged. The wall is not hiding. It is not past the horizon, not beyond the last galaxy. There is no mathematical slot for it to occupy. An edge to space, a place where distance itself stops, is not something general relativity forbids so much as something it cannot even write down. Stephen Hawking owned the definitive sentence here, and he used it for decades whenever the question found him. Asking what lies beyond the edge of the universe, he would say, is like asking what lies north of the North Pole. The question is grammatical, it passes, it feels like it is pointing at something, and it points at nothing, because north is a direction that exists only on the way to the pole and is used up entirely upon arrival. There is no defective region north of the pole, no censored zone the maps decline to show. The direction itself terminates, and the question dissolves with it, not answered, but discharged. Beyond, Hawking meant, may be exactly that kind of word, a direction that exists only inside the universe, spent completely by the time you have said the word everything. Hawking did not stop at space. In 1983, with the physicist James Hartle, he proposed that time itself may close the same way, in what became known as the no-boundary proposal. The Big Bang has always presented the same problem as the universe's edge, transposed into history, a first moment with an apparently exposed rim, inviting the question of what came before it and what lit the fuse. Hartle and Hawking's mathematics suggests that near the beginning, at the scales where quantum mechanics governs space-time itself, the distinction between time and space dissolves, and time, traced backward, does not run into a wall or an ignition point. It curves, smoothly, the way the Earth's surface curves at the pole, becoming just another direction of space, so that the universe's beginning is not an edge but a rounding, a southernmost point on a globe of space-time, complete, closed, with no rim in the past for a cause to reach through. Asking what came before the Big Bang, on this proposal, is asking what is south of the South Pole. The universe, Hawking liked to say, would be entirely self-contained, without boundary in space or time, neither created nor destroyed. It would simply be. The proposal remains one live option among several in quantum cosmology, contested like everything at that frontier, but it completes the picture number one has been assembling. Not just no wall out there, no door behind us either. It is a strange comfort of intellectual history that a North African bishop reached the shape of this answer 16 centuries early. Augustine of Hippo, pressed around the year 400 by mockers asking what God was doing during all the eternity before creation, refused the question's premise in his Confessions. Time, he argued, is a feature of the created world, brought into being with it, so there was no before for anything to happen in, and the question, however sincerely asked, refers to nothing. Cosmology's modern books quote him with a kind of family pride, because whatever one makes of his theology, the logical move is exactly the one physics found itself needing, the recognition that some questions are not deep, but merely shaped like depth, grammar running past the edge of its jurisdiction. What is outside everything? What came before the first moment? What is north of the pole? The form is a question. The content, perhaps, was never there. And yet physics, honestly told, has not fully earned the serenity of that dissolution, and number one keeps its final unsettling twist in this gap. In 1982, Alexander Vilenkin, whose name has attended half the theories tonight, published a short paper with the almost impudent title of Creation of Universes from Nothing, showing that quantum cosmology permits a universe like ours to tunnel into existence, the same tunneling we met at number 2, but from a starting state with no space, no time, no matter, and no energy, a state that is not an empty container, but the absence of the container itself. The mathematics goes through. And it leaves standing the one question that may survive every dissolution on tonight's list. The tunneling obeys laws. Quantum mechanics wrote the rules by which the nothing gave way, and if there was truly nothing, no space, no time, no substrate, then in what sense were the laws there to do the governing? Where does an equation live when there is nowhere? The physicist Lawrence Krauss built a best-selling book on the physics of nothing in 2012, and its fiercest critics, philosophers and physicists alike, pressed exactly this point, that every nothing physics has ever used is a something wearing careful makeup, a quantum vacuum, a set of laws, a mathematical structure primed to give birth. The disagreement was never resolved. It may not be resolvable. The universe may be self-contained in space and self-contained in time, and still owe an unpayable debt of explanation for the rules themselves, and that debt has no address to be delivered to, no beyond, no before, no outside, which is, if you sit with it, the purest form of the question this whole video has been circling, stripped at last of every picture. There is a photograph worth holding in mind as this answer settles, because it makes the geometry of our situation physical. In 2004, the Hubble Space Telescope stared at a single patch of southern sky for the better part of 1,000,000 seconds, a patch chosen for its emptiness, about 1/10 the width of the full moon, the size of a grain of sand held at arm's length. The resulting image, the ultra-deep field, contains roughly 10,000 galaxies, and its successors from the James Webb Space Telescope go deeper still. Galaxies whose light left them when the universe was a few 100 million years old, crowded into a keyhole of darkness a fingertip would cover. Every one of those 10,000 galaxies sits at the center of its own observable universe, its own sphere of 93 billion light-years, and nearly all of each sphere lies outside of ours. The grain of sand patch, in other words, contains 10,000 centers of everything, 10,000 complete skies, each one wrapping its holder as seamlessly as ours wraps us, none of them an edge, none of them at an edge, each of them a middle. Multiply by the whole sky and the arithmetic dissolves the question all over again. The universe is not a territory with a frontier somewhere out past the last surveyed galaxy. It is an unbroken field of middles wherever there is someone or something to stand, and the only thing anywhere that resembles an edge is the private, portable horizon that attends each middle like a shadow. That, in the end, is what the mainstream answer asks you to trade. You give up the wall, the container, the room beyond the balloon, every picture the question came wrapped in, and you receive a universe that is all interior, a cosmos of pure middle, where every possible observer, on every possible world, in every era of the universe's life, looks out and finds themselves at the exact center of everything they can know, equally, forever. No vantage is privileged, and none is peripheral. Nothing in existence has ever stood at the edge of the universe, not because the edge is guarded, but because being somewhere is what rules it out, and everything that exists is somewhere. The question this video is named for turns out to describe the one experience the universe cannot offer anyone. Take the journey one last time, then, knowing what we now know, you leave Earth with unlimited speed and unlimited patience, determined to do the thing directly, to fly until the universe runs out and see what is there. The Milky Way falls away. The local group scatters behind you like harbor lights. You pass the galaxies whose light filled the deep fields, young and violet and forming, and you keep going, out past every object any instrument of ours has ever recorded, chasing the place where the map went pale. And the night does not thin. Everywhere you arrive, space is simply present, ordinary, generous, hung with galaxies in every direction, and every direction includes a head. You fly for 100 billion years. The stars age and redden around you, and new ones refuse to stop forming, and at some point, in the middle of nowhere in particular, you cut the engines and admit what has been true since Earth. You are not approaching anything. There was never a wall out here, never a rim, never a pale region where space frays into whatever space sits in. You remember the number you left home with, 46.5 billion light-years, the radius of everything, the biggest number the night owned, and you understand it at last. That number was never the size of the universe. It was the length of your sight, the distance a lamp reaches down a road, and you have spent 100 billion years driving toward the end of lamplight, and the road never noticed the lamp. The edge you set out for has been behind you the whole way, riding with you, because the edge was made of seeing, and out here, where your old horizon is ancient history, some other watcher's horizon holds you at its rim, wondering what could possibly lie beyond. That is the return of the sentence this night began with, and you can hear how its meaning has shifted under the weight of the list. The edge is not a wall, it is a horizon of light. Hours ago that sentence was a reassurance, the friendly correction that no barrier hangs in the sky. Now it gives up its second reading, the one the finale was always going to collect. The horizon is the edge of seeing, and if number one is right, the edge of seeing is the only edge there has ever been, anywhere, at any scale. Every boundary this video has handled, the rim of the observable, the wall of the bubble, the horizon of the parent black hole, the screen of the hologram, belongs to observers and their limits, not to existence itself. Existence, on the mainstream answer, simply does not have the kind of outside that limits imply. The universe is not in the dark. The dark was in the question. Why does this answer sit at number one on a list of disturbing theories, ahead of drifting cluster flows and incoming walls of physics? Sit with it a moment, and you will feel the reason arrive on its own. Every other theory tonight, however cold, left you a somewhere. The copies of number 10 live in real galaxies. The parent universe of number 4 has weather and astronomers. Even the bubble of number 2 is at least an event, a thing that happens in a place. Fear of what the outside contains is, in the end, an ordinary fear, the oldest one, the one our ancestors aimed at the dark past the firelight, and every monster it proposes is a kind of company. Number 1 takes the company away. There is no dark past the firelight. There is no past the firelight. The universe is not a camp in a wilderness. It is the whole of the wild, and the whole of the camp, and the whole of the concept of location, with nothing left over, and every mind that has ever felt watched by the beyond, or beckoned by it, or small before it, was feeling something about a direction that does not exist. The vertigo, when it lands, is not the fear of something out there. It is the discovery that out there was a story we told, and existence, all along, has been complete, sealed not by a wall but by the absence of any place a wall would separate us from. But lie still with that vertigo for a minute, in the dark, at the end of this long list, and notice what it turns into. A universe with no outside is a universe that cannot be intruded upon. Nothing looms beyond the horizon, because beyond is not a place. Nothing is missing from existence, because there is no elsewhere holding what we lack. The completeness that first feels like a locked room slowly reveals itself as the opposite, the end of all locked rooms, a totality resting on nothing, because it needs nothing, self-contained the way a sphere is self-contained, not deprived of an edge but perfected by the lack of one. Augustine's answer and Hawking's turn out to share not just a logic but a mood, and the mood, approached slowly enough, is peace. The universe is not adrift in a void. It is not a bubble in something colder. It is everything, being everything, requiring no shelf to rest on and no room to grow into, and you, tonight, are not stranded on a speck at the mercy of an infinite outside. You are a place where the totality thinks, one of the sites where everything that exists briefly knows that it does, asking after edges out of an old habit of skin, and finding, each time the question is asked carefully enough, only more universe, and then sleep. And so the list ends where the universe does, which is to say, nowhere, and that is the gentlest possible place to leave you. 10 theories, and the last one hands back every fear the first 9 raised, because whatever sits beyond the edge of the universe, copies or currents, bubbles or parents, holograms or walls or nothing at all, none of it has ever once reached into this room, and none of it can. The night outside your window is the same night it was 3 hours ago, the horizon of light holding steady at 46.5 billion light-years, the questions resting, finally, at the pole of themselves. Let the universe be complete tonight, with you inside it, exactly where everything is. Sleep well, and good night.